Right. Welcome to the RQI Circuit 2026. This week we're here in York for the 7th local edition of the RQI Circuit. So the RQI Circuit is this series of local conferences that happen at different RQI hubs every week, every Friday, basically. They're going to keep going until July 31st, when we're going to have an online edition. Next week we'll be in China. Welcome to the RQI Circuit 2026. This week we're here. So we're going to be in China next week. This week we're here in York. So this is a local effort put together by the International Society for Relativistic Quantum Information, the ISRQI. So if you're interested in this research, feel free to take a look at the webpage. This is the webpage. It's isrqi.net. If you want to register, you can scan this QR code, or if you go to the webpage, you can click here, this little key, and this will bring you to a registration thing. So feel free to do that if you're interested in this research and all of these things. So let me give it to the local organizers. So the local organizers here are Patricia, Christiane, and Filippo. So please, the floor is yours.
Okay, so first of all, thank you everyone for coming, everyone who agreed to participate and give a talk at the RQI Circuit. Again, we are the local organizers, so if something goes wrong, you know who to blame. But other than that, I would like also to thank Rick, who has come all this way just to take care of the broadcasting. And also our sponsors, who are essentially the people who are paying for coffee breaks and making possible that you will all have lunch today. And they are basically the Department of Mathematics of the University of York and the Research and Culture Fund. And special thanks also to Alexandra Lanot, who has been incredibly helpful in the organization of this conference. So without further ado, I think we are ready to start. So let's thank and welcome our first speaker, who will be Chris Fewster. Okay, let's go.
Excuse me while I put this furry thing into position. Okay, so I hope that's coming through for you, Rick. So, okay, well, it's a great pleasure to speak here at the circuit, and thank you to the organizers for the opportunity to speak here. So I'm going to talk about work in the measurement framework for quantum field theory that I've been developing for a little while now, originally with Rainer Ferch and also with many people here. But I'm going to focus particularly on work with Christiane Klein, which will be continued in her talk, which comes next. And this is about polarization measurements in quantum field theory. Okay, so time is limited, so I'm going to keep moving. And I did have a slide about the woes of measurement in quantum mechanics, but that had to get cut. So I'm just saying, adding to the well-known woes of measurement in quantum mechanics, among which, so insert your own list, but among them, the one that gets my goat is the idea that there is a projection postulate and a state collapse that is somehow instantaneous. Because it is very clear when you move to the relativistic regime that this has to lose any meaning that it even might have had, which I claim it doesn't really, due to the relativity of simultaneity. Okay, so clearly we have a problem with that. And furthermore, if you try to make a relativistic version of instantaneous collapse by saying, well, maybe there's some special hypersurface across which the collapse occurs, this attempt fails, as has been known since work of Aharonov and Albert, who were criticizing a little bit what Helvig and Krauss said, though it's not quite clear that Helvig and Krauss meant quite what Aharonov and Albert criticized, but that's another matter. The point here is that attempts to specify a surface for collapse is also problematic, even in flat space-time. And of course, if we go to curved space-times, things are even worse because there are no preferred time coordinates and no preferred foliations. People have tried, of course, over the years to simply extend the rules of quantum mechanics by hand to quantum field theory, and there are well-known problems that occurred when trying to do that as well, of which one of the most famous is the Sorkin problem of superluminal communication arising from apparently reasonable measurements. So he concluded that these apparently reasonable measurements were impossible. So instead of all of that, what Rainer Ferch and I decided to do a few years ago was to try to model the measurement process. And in this way, we were combining two things: quantum measurement theory, as it's developed over the years, particularly as represented by this book of Paul Busch, Pekka Lahti, Juha-Pekka Pelonpää, and Jari Lienen, and on quantum measurement, which is a very nice and comprehensive book on quantum measurement. It describes the measurement chain, particularly in quantum mechanics, but you will not find anything in that book on quantum field theory. On the other hand, we have this book here, which is a sort of update of Haag's classic local quantum physics account of algebraic quantum field theory. So if you follow that line of work, you find a very nice conceptual and clean approach to quantum field theory, but traditionally there was next to nothing said about measurement. And our idea was to put these contrasting color schemes together and describe the system, probe and coupling that you would find in the quantum measurement side of things, to describe all of that in terms of algebraic quantum field theory. So that was our starting point, and that's what we actually have done. Okay, so it is all framed in terms of algebraic quantum field theory, which in York is breakfast talk, but maybe not everybody listening online has the same advantages that we do, and therefore I'm going to say a little bit about what algebraic quantum field theory is. So at least for this talk, this is all you need to know. And the idea is that a quantum field theory is described through its observables, and those observables form a star algebra, and a star algebra is simply a mathematical gadget in which those observables can be combined by linear combination, they can be multiplied through the algebra product, and you can take an adjoint, a star operation that of course flips the order when you have a product. So it's actually something that you know very well. The simplest example would be a matrix algebra, okay, is a star algebra. And we also assume that there's a unit, as there is in the matrix algebra case. Okay, on top of that, we take the view that observables should be local things by and large, and so to every space-time region O of a suitable type, there will be a subalgebra of the algebra of all observables that describes those observables localizable in the region O. And then there are some assumptions on top of that, not so very many, that I will need. One is that we have what's called isotony, and that says that if I have one region contained in another, then the corresponding algebra of local observables is contained in the algebra of observables for the larger region. So that's the isotony axiom, and I am going to assume also that the full algebra is actually the algebra of observables for the whole of space-time. Okay, one could imagine something slightly different, but I'm not doing that today. Second assumption is what's called the time slice axiom, and it says that if we have one region O1 inside another, but this one, O1, is big enough that it's got a Cauchy surface of O2, then it's not just an inclusion, it's an equality we have here. So I need to explain what a Cauchy surface is. This is simply a set on which you could pose initial data for a wave equation. Okay, so it's like a time zero surface in Minkowski space, or a constant time surface in Minkowski space. In general curve spacetimes, we have this idea of a Cauchy surface. So what might we find in one of these local algebras? Well, the ones that are self-adjoint, in the sense that when we apply the star, we get back to the operator A, those are going to be regarded as observable within the region O. And a typical example of that would be if we have a quantum field and we integrate it against some function that vanishes outside the region O. So that would be a very typical element that we might find in such an algebra. We also write states in a funny way if you come from the more quantum mechanical tradition. Here we regard a state as a linear map from the algebra of observables to the complex numbers. Okay. The aim of this map is to assign expectation values. Okay, so we write omega of whatever is the expectation value of whatever in the given state. And there are only two conditions here. If we give it the unit, which is an observable that always takes the value 1, then we should get expectation value 1. And if we feed in an observable that kind of looks as though it should be positive, then the expectation value should indeed be non-negative in this way. This is not a particular species of quantum field theory. The idea is that all quantum field theories worthy of the name should be representable in this way. Because if a quantum field theory doesn't have observables that you can talk about, then I'm not quite sure what its utility is. Okay, so that's the idea underlying algebraic quantum field theory. So when we come to the measurement schemes, the idea is the following. As ever, when talking about measurement, you have a system that you're interested in measuring. That's going to be a quantum field theory. To measure it, you bring along a probe. That's also going to be a quantum field theory, and you couple them together. So that means that we change the physics of just having the two original theories and get another theory, which is somehow the two of those but coupled together. That is also going to be a quantum field theory. Okay, so everything is going to be described by quantum field theories as set out in algebraic quantum field theory. And in particular, we're going to compare the sort of uncoupled combination where we simply take the tensor product of the two theories, so no dynamical interaction between them whatsoever. We compare that with a coupled combination, and that's where the physics is different within some bounded coupling region that will be denoted K. Okay, so that's the idea of coupling them together. At initial times, there's no coupling. At late times, there's no coupling. So also, I'm not telling you in particular what does happen inside the coupling region, merely something does, and it is describable by quantum field theory. Okay? Of course, you might design your own idea for what the measurement coupling is, and when we come to the polarization part, then I will be saying something about that. But as an abstract setting, we don't need to assume anything except that where the coupling is off, it's off. Okay, that is the only thing that is assumed here. But already, if you put that together with the assumptions that we've made, particularly these isotony and time slice axioms, we can infer that there are correspondences between the uncoupled theory and the coupled theory. And there's one at early times, before the coupling was switched on, and there's one at late times. And these are going to be denoted Tor plus and minus, minus for early and plus for late times. And if you put them together in this way, so you first go from uncoupled to coupled using the late time identification, and then back again at using the early time identification, this is what we call the scattering map. It is a map from the uncoupled combination to itself. It is an isomorphism, and it respects algebraic operations, so it's what we call an automorphism of this uncoupled theory. Okay. Now, the idea is something that's quite familiar from quantum mechanical measurement theory. We prepare the system and the probe at early times in particular states. So the system is going to be in state omega, the probe is going to be in state sigma. At late times, we make a measurement on the probe. And for example, we might choose a probe observable B. Then, what we showed was that this is tantamount to measuring something in the system. Okay? And the something in the system is what we call the induced system observable. And I'm not going to dwell too much on this in this talk, but there is a formula for what you get, and it uses of course, the observable you're trying to measure. It also involves the scattering map, and finally it involves this thing, eta sigma, which is essentially tracing out the probe using the probe state. Okay, so this gives you a map from probe observables to system observables, And why is this the same as measuring the probe observable? Well, we have what we call value reproducibility. The actual experiment is done on the coupled system. Okay, that's what we actually have in a lab. And there is an expectation value for the outcome of that. That is the same as the expectation value of this induced observable in the system state. Okay, so this is the sense in which we can say that this measurement scheme measures a system observable. Okay, value reproducibility. If I have a full-length talk, then I spend some time talking about the good properties that this has. But I want to focus on states, so I'm moving on straight away. And here, I'm going to focus particularly on binary measurements. Yes, no, true, false, fail, oh, no, success, failure type measurements. And these are modeled by what we call effects. And those are operators in your algebra that are positive, so E is greater than or equal to 0, but they're also bounded above by the unit, which, if you think about it, means that 1 minus E is positive. So E, meaning the original effect, and 1 minus E, which is not E, if we want to interpret it like that, are both effects, they're both positive operators, and we interpret the expectation value as the probability that this effect comes off, okay, that the test is satisfied. So what we do now is the following. We consider an effect E of the system and another one F of the probe, and we prepare the system and probe at early times, we couple them together, and then we test the coupled system for those two effects at late times. So there are 4 possible outcomes. You could have E and F both satisfied, E but not F, not E but F, and not E and not F. So there are 4 possible things. We can compute the probabilities for all of them. And here I've given the probability for E and F, and it works like this. We need to turn the E tensor F, which is the combination of these two in the uncoupled system, into an effect in the coupled system. We use the late time identification to do that. We also have the combined state of the system at early times. For the uncoupled theory, we need to convert that into something for the coupled theory at late times, and we need to convert that into a state on the coupled theory. We use the early time identification to do that. When you put them together, we see that we have this combination of the TORs, which gives us the scattering map. And so again, everything can be expressed in terms of the scattering map. Okay, so we can compute all of those probabilities. So suppose that the test on the probe is successful. Okay, you measure it, it comes off. In that case, we still have the E test on the system to go. But the probabilities of that can be conditioned on the success, because that's something that's happened, right? That outcome has been registered. And so we can compute the probabilities using the conditional probability formula. Okay, the ratio of the probability of both of them happening divided by the ratio just of F happening. So that conditional probability is the one you would use if you know the F outcome in order to predict the E outcome, right? If you're placing a bet, that's what you would use. And you would use that if you were aware of the outcome, or even, frankly, if you suspected it. Maybe you can influence, maybe you have a friend who can ring up the president of FIFA and get something changed. You can somehow, without things being entirely as they should be, you might be able to influence probabilities, okay? And so you would use this conditional probability, okay, if you are reasonably sure of this as an outcome. So, an interesting question is whether there is a state of the system that actually gives you those probabilities? Okay? And the answer is yes, there is. And it's very simple, because if I'd actually written down for you the formula that expressed those ratios, it is actually defining a state. This is a minor miracle, but it is really important, because it tells you that there is a state that gives you the probabilities that you could otherwise get by taking a conditional probability. So in other words, the new one builds in the information you got by doing the measurement. So it's the right one to use, and we can also do non-selective ones. A very important thing is this was derived rather than being asserted. So, what are some properties of this thing? We have a nice explicit formula, and if we do updates at space-like separation, a standard question is, well, which one do you do first? Because there's no absolute ordering of these two. Well, the good news is it's consistent. You can do these updates in either order and you will get the same result. Also, if you look at an observable that is localizable space-like to the coupling region, then it turns out that the non-selectively updated state gives you the same expectation as the original one. In other words, nothing changes in that expectation, which is just as well, because this observable shouldn't even know that there was a coupling. It's space-like separated from it. So I call this the principle of blissful ignorance, for obvious reasons. That is about non-selective updates. If you have a selective update, the answer can change, but it changes if and only if there are correlations between the observable that you want to measure and the induced system observable for the other measurement in the original state. In other words, the change is because there were correlations. And this is something we're even familiar with in classical probability theory, so there is no surprise here. But you might think, well, if that's all that's going on, is this going to manage with Bell inequalities? Okay, because maybe this all sounds a little bit too much like classical probability. We'll come back to that. An important point that I want to make is that if you have two regions at space-like separation, then one can actually prove that the probability of A2 given A1 is the same as the probability of A2 updated in the updated state, updated conditioned on the success of A1. But by symmetry, the same is true in the other order as well. And so the probability of A1 given A2 is given by the probability of A1 in the updated state for A2. Now this is interesting because it means we've got two updated states on the loose. Okay? We've got the one when you update on conditioned on the success of A1 and the other one when you update on the success of A2. And these are both useful because they give you different conditional probabilities. A1 conditioned on A2 or A1 conditioned on A2 or the other way around. Okay. So this really casts a bit of light on whether or not state update is some absolute process, right, that everybody would agree on, or rather more, it's a relative concept. So if you know the A1 result, you do the A1 update, and that allows you to predict A2. But if you know the A2 outcome, you do the A2 update, and that allows you to predict A1. So these are not necessarily absolute processes. It feels much more as though it's a relative concept. So now in the last couple of minutes, I want to come to the polarization sensitive measurement that I mentioned before. Of course, in actual quantum optics experiments, people use photons. There is a clue in the name. And these often use polarization measurements, beam splitters, polarization rotators, and so on. We were thinking, well, how can we work with these things and get models of them? There are some complications if you use electromagnetism, one of which is gauge freedom. And the other is that actually optical devices often use electromagnetism in media. Okay, so it's not vacuum electromagnetism, it's a like more complicated version. So instead we decided to use the Proctor field, which is a massive spin 1 field. So it models the W bosons and the Z bosons in particle physics. I am not proposing that people do Bell experiments with W bosons. I am just saying that this is a way of illuminating the conceptual point here. But a useful thing is certainly that the charged Proctor field can be manipulated directly by external electromagnetic fields. So I now have a couple of slides about the Proctor equation and how you solve it. I think I'm running low on time, so all I'm going to say is that usually that it isn't as obvious as solving a wave equation. I mean, not everybody thinks solving the wave equation is that obvious either, but once you get to a certain point, you realize that solving the wave equation is okay. The Proctor equation is not like that because it's got some extra second order terms, and so you use a trick. But the trick doesn't actually work very well beyond the original setting of the uncoupled Proctor field. So what we did, myself and Christiane, was to develop an auxiliary field method. We add some extra fields and then we're able to solve the Proctor equation. And I'm going to skip over this, I'm afraid, except to advertise our paper. So coming to the model that we looked at the charged Proctor field coupled to a charged scalar field. So if there's the Lagrangian for the Proctor, there's the one for the scalar, and here is the coupling. V is going to be a compactly supported covector field. And that is what couples the field together, the two fields together. When it's 0, there's no coupling. When it's on, they are coupled, but this is sensitive because we've got the dot product of V and W to particular directions, if you like, of the W field. And that's what gives us the polarization measurement. So all of this says we can deal with it. And now I want to come to the application. In Minkowski space, what we can do is set it up so that this coupling is along a particular direction like so. We then fired in an n-particle state where we've encoded a qubit into the polarization vector. So right here we have S is the one particle state. It's some scalar function depending on momentum multiplied by a polarization vector. And when we do this, we can find what the expectation value of this probe observable is. We find vacuum noise. We of course have higher corrections, but at lambda squared there's a factor saying how many particles we've got. And here we see the quantum mechanical transition probability. Okay? So this is what you would get if you were just doing quantum mechanics for polarization. And then there's another factor, which is a form factor describing the detector. So we have got as far as 1809 because we have proved Malu's law in quantum field theory. And I'm going to conclude with, just leave this up and move to questions. Thank you for your attention.
Thank you, Chris. Are there questions from the in-person audience? I see one there. I'm going to move to you with this microphone, and I hope it will be picked up.
Thank you. Thank you very much for your talk. I just want to caveat I'm an experimentalist, and so maybe my understanding of all the mathematics is not quite up to following every aspect of your talk. But I specifically want to ask about the polarization measurements. When you were the slide you had up with the different ways of measuring in the optical regime, and you mentioned about the challenges of the electromagnetic field. Yeah. My research is a MEV scale, so we actually in gamma polarization measurements, which obviously we don't use any of those optical kit either, and we do indirect polarization measurements through Compton scattering. Would your mathematics and formula be able to sort of account for indirect measurements of polarization, such as a Compton scattering that doesn't use the electromagnetic field beam splitters and things?
Yeah, it ought to do that, yes. So it's a question of what you model, right? So we have system and we have probe. So in this instance, the system would be the electromagnetic field, and the probe would be electrons, right?
Yeah.
And so you would have your initial electrons in some incoming beam, I presume, and then you're measuring where they get scattered to. And you're actually measuring something about the electrons, and you're inferring something about the gamma rays.
Yes.
So that really should fit into this framework.
Okay, thank you very much.
Yeah.
Further questions?
Hi, Chris. Thanks for the talk. It was really interesting. You used the term late time a few times throughout the talks. I'm a little confused about what that means exactly. So we have our initial state preparation, and then we measure our probe at some late time, and then we witness a late time effect. But what does that actually look like?
Yeah.
Do we just allow the system to evolve at arbitrarily long scales, or is it just any evolution?
Right. So here we have a particular coupled evolution in mind, and remember that's only switched on in a bounded region of space-time. Okay. So like that coupling I had with the polarization, there was actually there was a factor rho, which I didn't talk about, but that is where the switching on in some compact region of space-time happens. What late time means is anything that isn't in the causal past of that region. So unfortunately, we don't have anything I think I get told off if I draw on here. But essentially, imagine that you've got the little region where things are switched on. Anything outside the past light cone of that region is going to count as late time. What I mean by early time is anything outside the future light cone of that thing. So in such a way, I managed to say what early and late mean without ever writing down any time coordinates.
Okay. Yeah. All right, thank you.
Are there any further questions from the audience? I see one from Rick, so I'm going to run. Oops.
So I was actually very interested in the part you skipped of your talk regarding the strategy for solving the Proc equation coupled to an external field. So would you mind giving some details now?
Okay, I can do that. Well, thank you for giving me the excuse. So I will just, I won't go through what the usual trick is. Okay, I will just go to the remedy. And here is our Proc equation. And remember that the problem was that it's not got the second order piece that looks like a wave equation. I've written this using differential forms because it's much easier to see what happens. I apologize to people who don't know differential forms. But what I do want to say is that this is, if you like, a bit of the wave operator. And here I've got all of the wave operator. And I've just smuggled that in by adding this bit and then compensating by adding this here. And so phi has come out of nowhere, but if phi is equal to delta omega, you see I've just added and subtracted the same thing. But the good point is that I now have something with the wave operator. What does phi do? Well, if I think about it a little bit, I realize that phi has to satisfy this equation here, okay, in this instance. So, and these two together, because this has got the wave operator and that is actually invertible, I can solve that system. I can find green operators for it, advanced and retarded, for that system. For both phi and for phi and w. Now, meantime, this side equation, this side condition, turns out to be preserved under the evolution, all right? Because actually the difference between phi and delta omega obeys its own hyperbolic equation. So if it vanishes at early times, it vanishes everywhere. If it vanishes at late times, it vanishes everywhere. So that's the strategy, and that means that the original system where we not only have these two equations, but that side condition as well, this has green operators. And we have this in much greater detail. So we have great big commutative diagrams and so on, conditions under which you can take something that looks like a Proctor system, extend it by adding extra fields with side conditions, and get green operators out. Okay, so that's what's in our field, in our paper, and in particular, the one I'd advertise is that we can do arbitrary anomalous magnetic moment Proctor, which is something that some papers will say is not possible. It's not possible by their methods, it is possible by ours.
If there are any further questions, if not, we're going to move on to the next speaker. Thank you, Chris, once again.
Yeah.
So, the next speaker in our morning session is Christiane Klein, also from the University of York, who's going to tell us about quantum field theory models for testing Bell inequalities.
Yes.
Please, Christiane, take it away.
Yeah, thank you, Daan. Thank you all for coming. So I will basically continue where Chris left off with a little bit of a recap in the beginning and a bit of motivation for looking at Bell inequalities in this framework, even though I think Chris has given plenty. As he said, quantum measurements are a host of problems, and one way to look at them is to do an operational approach and construct a measurement scheme that tells you how to take a system and a probe, smush them together in some way, then read out the probe and learn something about the system. And in particular, this scheme should tell you what information of the system do you learn by looking at this quantity of the probe, and also how does this measurement affect the system. And as Chris said, that is a relatively recent development in quantum field theory, even though in quantum mechanics this has been around. Let me briefly recap how this development looks in quantum field theory. As Chris said, we are going to look at quantum field theories in the terms of algebras. So these curly letters will all be algebras in my talk. So we will use a probe algebra to investigate the properties of a system algebra. The uncoupled system and probe A tensor B will agree with a coupled system where the full coupled dynamics are at play outside of a compact region K, which is where the coupling takes place. And I've actually drawn some diagrams over here. So this is my space-time, and this bit in the middle is where the coupling takes place. And then to come back to your question, what are early and late times? So here you can see this would be early times, this would be late times. And on these early and late times, we have these invertible star homomorphisms. So invertible maps between the star algebras that describe our system and probe, uncoupled to the coupled. And if we combine them, we get this scattering morphism, which goes from the uncoupled to the uncoupled theory. So it's a map on U that implements the coupled dynamics on this uncoupled system backwards in time. Okay, how does a measurement work in this thing? Well, as we said, we prepare early, so our initial state will be some product state. We prepare our system, we prepare our probe, and then we pull this to the coupled algebra where really the measurement happens using this map tau minus. We measure late, so the observable that we look at in the probe is some B that lives in the algebra located here, and then we tensor it with a 1, and we move it to the coupled algebra again, but now using this tau plus. And then we want to learn, of course, some information about the system in this coupled region K. And how do we do this? We find this induced observable that satisfies this equation. So our observable that we measure in the state that we prepare should equal the expectation values of this induced observable in the system state omega. And it turns out, as Chris has said, that this is the partial trace over the probe system of this scattering map acting on one tensor B. Okay, and then the last bit is what happens to the system. Well, Chris just explained in very nice detail that you have the state update formula, so if B is an effect, a yes or no question asked, then this is how the updated state that gives you the condition probabilities, if you know the outcome of B, looks after the measurement. And this is, as I said, derived from conditional probabilities for effects. And as Chris has alluded, maybe this is all a bit too classical. What about Bell inequalities? Can we still violate them with this? And if we want to look at this, there's one particular scenario that we wanted to look at, which is the Clauser, Horn, Shumini, and Holt. And the experimental setup that they look at, more or less, so you have two space-like separated polarization measurements, usually done with photons or some polarized atoms or electrons. And for simplicity's sake, we want to use our procoscalar model that Chris has just introduced for polarization-sensitive detectors to model this CH-SH scenario and see if in this framework we can actually find violations of the Bell inequality that corresponds to this scenario. But before we do this, I should also briefly recap this procoscalar model. So we have our probe. Our probe will be a simple scalar field, so it will live on this bundle. This is really just, it's a function. It's a scalar function. And this is just multiplication. And we have the Klein-Gordon operator, which acts on the scalar function, and we give it some mass m. And as Chris has said, this is a very nice operator. It has so-called retarded and advanced green operators. We kind of know how to solve it. And we also kind of know how to quantize it, how to construct an algebra that represents this classical theory in the quantum realm. The Proctor field lives on this bundle. It basically means these are covector fields. And here's sort of the obvious metric, which is just the metric of the spacetime. The Proctor operator we've just seen. Note that we can choose a different mass for the Proctor field than we have for the scalar field. So this is one thing you might want to tune if you want to improve your experiment or improve this model of the experiment. And as Chris has said, it's less obvious, but this also has these retarded and advanced green operators, so we know how to solve this theory and how to quantize it. So the coupled theory is we add a bilinear coupling, which is controlled by this real covector field V. And then if we write this coupled operator in this matrix form, where W is our Proctor field and phi is a scalar field, then it looks like this. So on the diagonal, we just have the Proctor operator and the Klein-Gordon operator. And on the off diagonal, we have the multiplication by V, or the inner product with V, essentially. Again, we can show that this has green operators, advanced and retarded green operators. Something that Chris, I don't know if he mentioned it, we can extend this to multiple scalar fields. That is relatively straightforward. Basically what happens is these become also vectors, and this becomes also a diagonal matrix. That is basically all that happens. It's a bit more bookkeeping, but otherwise not much more complicated. And last but not least, one thing that we will need is this classical scattering map, which we will use later to implement this scattering map, large theta, on the algebra for this theory. Okay, and I should also say one thing about the quantization in this particular case. So this is one way to construct the algebra if you have a theory that is described by a field that follows equations of motions that have these green operators, is you can construct your algebra by basically just you take the smeared fields and finite sums of finite products of these. So that's the freely generated algebra bit. And then you throw out everything that follows these relations. So the phi's are all linear. You know how the star involution works, so you know what adjoint means, which is just adjoint of this one is this one. They should satisfy the field equation in this sense. So if you smear them with something that has the operator acting on it in a weak sense, this should give you 0. And then you have the usual commutation relations, which in curved space-time means that you put the advanced minus retarded green operator, and then you take the inner product of whatever functions you smeared your fields with. And you can convince yourself that if you go to flat space-time, equal times, this actually gives you the right commutators that you're used to. And as I've alluded to, in this particular setup, we can implement the scattering morphism theta, which acts on A0, which is really the free algebra. Because if you set V to 0, you just get the free theory by taking phi of H plus F and giving you phi of this classical scattering map acting on H plus F. Okay. And if you want to go to multiple fields, again, this is a really easy fix. Basically, everything stays the same. The only thing you change is that now these F's are vectors of functions. So you have multiple functions. Okay, so now we can go to multiprobe measurements. And the setup is, again, we work in Minkowski space because that's the easiest thing to do. And we couple our Proctor field, which is our system, to n complex scalar fields, which are our probes. So now we have multiple probes. And then we look at the scalar fields, we put them all in the vacuum. And the Proctor field, we can put in some state psi, which is the superposition of two states. And what these states are, they're basically just n excitations of Proctor particles and n prime excitations of Proctor antiparticles, because we're in the complex Proctor case, with some functions s and t that are in this ugly space here, which is just the one particle Hilbert space for the Proctor field. So for scalars, you can just forget about all this. It would just be square integral functions on R3. And you need these bits for Proctor. And what we want to do is we want to compute the joint probability distribution for the outcomes of measuring this quantity here. So theta acting on phi 0 plus fi star, phi 0 plus fi. So this should be positive observable. And these fi we will choose so that all four of them, or all of them that we choose, are mutually commuting. So either each of these fi is only non-zero in one of the different Proctor fields, that's one of the different scalar fields. So basically each of them registers in a different scalar. Or we can space-like separate them. That would work as well, because then they also should commute. Okay, how do we compute this joint probability distribution? We start from a generating functional. So we take the expectation value in this product state psi, which was this superposed excited Proctor state with a Minkowski vacuum for all our scalar fields. And then we take the expectation value of the exponential of minus some factor mu times this phi star phi. And here I'm being a bit sloppy with the notation. From now on, if I write fi, I really mean 0 plus fi. But this is just a bit shorter. And what we find is we can do some basically notation where we cram all these factors into a matrix. Just it has all these factors on the diagonal. And this Nij is the inner products in this one particle Hilbert space now of the Proctor field and of our scalar fields of theta f. Again, remember there's like an invisible 0 there. And then mapping to the Hilbert space, which is basically nothing else but doing a Fourier transform and then restricting to the mass shell. So this is nothing else but the vacuum expectation value of our observables phi, or the vacuum correlations of phi I, phi j. And with these, we can then express this G as a sum which goes from 0 to the number of Proctor particles plus Proctor antiparticles. And then C is some polynomial function of our factors mu I and of these single mode, single scalar results that Chris presented. So in particular of these form factors that were mentioned and of this qubit, quantum mechanical qubit results. So they are all here in this C, they and some powers of them. And then this is divided by the determinant of 1 plus the matrix product of these matrices M and N. So what goes in here is our factors mu, and again, these vacuum results. And then we take this to some power R plus 1. Okay, to get to the joint probability distribution from there, we need now to take the inverse Laplace transform of this generating functional in these factors mu I. And for m equals 1, so m equals 1 means that this matrix thick m is now just mu, and the matrix thick n is also now just a number, namely the vacuum expectation value. We can do this, and you get some, and the parameter that we call, so x would be the outcome of your measurement, and the probability is then has some inverse exponential, so it's exponentially decaying, and then there's some polynomial growth with some factors that you can determine. For m equal 2, you can also do this explicitly. You get something called a bivariate Kibble distribution. It has a similar form, but there are some additional functions that you get that suppress the exponential growth. And for m bigger than 2, so now you have really 3 or more probes, you can still do this. You get a series expansion for a multivariate gamma type distribution that in certain cases we know does converge, but there's no closed form anymore. So this seems rather complicated because we're really in this last case, because remember we want to do two channel detectors at space-like separation for the CHSH setup. So what can we do? Well, there's some simplification. If the off-diagonal elements of this matrix Nij, so the correlations of the phi I, phi fi, phi fj are 0, then this generating functional factorizes, which means that instead of really having to do a 0, 1, okay, a multi-dimensional inverse Laplace transform, we just have products of one-dimensional inverse Laplace transform, which is much, much easier. So are we in luck? Does this actually happen? Kind of. So what we know is that for I not equal to j, these off-diagonal elements of this matrix, so these correlations, vanish to the first order in coupling if we set up our different coupling covectors to be in the same spot. So in particular, they also have the same smearing, or the same localization function, but they're orthogonal to each other. And also we have to choose these functions fi and fj, which smear our observables sufficiently nicely, and particularly sufficiently symmetric. So this is one way we can get rid of them. Another way is if the supports of these vi's and vj's are space-like separated, then these off-diagonal elements, as one would expect, are exponentially suppressed with respect to the separation. So the further we move them apart, these Nij go down exponentially in the distance of the two coupling regions. And so we can use this to at least approximately set them to 0 and make our life easier. Okay, so let's do this. And this is the setup we use for testing CHSH. So indeed, we will have 4 scalar fields. So now all our observable will be in one of these scalar fields only. And we have 2 pairs of couplings, basically, that are, each of these pairs are pairs orthogonal, and they're in space-like separated regions, which looks roughly like this. And then also we say that one of them we call the horizontal, which is at some angle to the x-axis. So our whole measurement will be in the xy plane for arbitrary reasons. The Proctor state will now be one particle, one antiparticle. The modes that we excite will be chosen such that the particle will be mostly going to one detector, the antiparticle will be mostly going to the other detector. And we're going to reject anything where we measure them at the wrong one. We choose the polarization such that these particle and antiparticle have maximally entangled linear polarizations. And what we detect, again, is these scalar fields squared. And we say that we have detected the Proctor particle or the Proctor antiparticle in one of the 4 channels that we have, so in one of the 4 scalars, if this is above a certain threshold B. So if this is large, we say we have detected something. If this comes out small, we say there was nothing there. Okay. And doing this, using this whole formalism that I just explained, we can then really compute the probability for detecting the particle in channel I and the antiparticle in channel J. And it looks like this. So it has this exponential suppression with respect to the threshold, which is not surprising if you have to get more result and your probability has this exponential suppression that I showed you earlier, then the higher I demand something to be to see something, the higher, the lower the probability to see something. It also depends on what I call the detector efficiency. So that's some factor between 0 and 1 that contains, among other things, 1 power of the coupling. So this should really be not close to 1, because if we're in the not close to 1 regime, then the approximation which it went in there, which is in particular that all these off-diagonal elements of this matrix Nij vanish, hinges on lambda being small. And then last but not least, it depends not on the individual angles, but on the relative angle of our 2 detectors. And then there's some noise terms, which also depend on P and B, but they're independent of the angles. And then following CHSH, we can compute this quantity E theta A theta B, which is just a ratio of these probabilities for certain channels. And what we find is that if in our setup, this is given by some function f, yes, times the cosine of 2 times the difference of angles. And the function f has the properties that it's between 0 and 1, and it goes to 1 as we push our threshold to infinity. So threshold to infinity means we're really rejecting a lot of things. So we basically want to get to the limit where we have no false positive measurements. We're not clicking ever if this is just vacuum noise. And then the CHSH inequality says, well, take different angle combinations, take the absolute value of this combination of these quantities E, and this must be less than 2 in a local hidden variable theory. And if you pick the optimal angles to violate this that you can get from quantum mechanics, which I think are like 45 degrees and 60 and 25 and whatnot, you can find them on Wikipedia. Then what comes out is that our result for this quantity CHSH is 2 square root 2 times this function f. And remember, f was between 0 and 1 and goes to 1 as we send our threshold to infinity. So in particular, we find violation of this inequality for f bigger than 1 over square root 2, which is really an extended amount of threshold parameter space. And we go to 2 square root 2 as b goes to infinity, which is the Cyrilson's bound, the maximal amount you can violate this inequality in quantum mechanics. So really, if we reject all the vacuum noise by making our detector incredibly inefficient, we get back to quantum mechanics. Yes, and that's basically the end of my talk. I hope I could convince you that Proctor can serve as a nice toy model for electromagnetism, with which we can play around, that we can show that actually this coupled Proctor scalar is green hyperbolic, and in this sense we can use it very nicely to test things in quantum field theory, and that we have a model in this framework for a polarization-sensitive detector that can indeed violate the Bell inequality, albeit very, very inefficiently. Thank you very much, and I'm happy to take questions.
Thank you very much, Christiane. Are there questions from the audience? I see a question from Rick.
Thanks for the talk. Super nice to see like the FV framework being actually applied to more concrete things and quantum information things, which is super cool. I'm interested in this threshold B that you have. Mm-hmm. I'd like to understand it a little bit better. So would you mind going back to the slide where you defined it in terms of the smeared phi I of Fi? Yeah, this, right?
Yeah,
so
well, that's not really a definition, but yeah.
Yeah, no, I mean, sure, it's not the definition, but I mean, sure, this is the definition, right? Yeah. So it's like how should I think of this, the observable, the phi I of Fi squared in the sense? Is this like the particle number here, or to some extent of your probe field phi I? What
this observable is basically a Paulman's, what people call scalar condensate or vacuum excitation. So what you would usually want to look at is phi star phi and then smear, right? Because that would really be like phi squared smeared. But then you would have to do renormalization. Mm-hmm. So this is sort of a Paulman's version of this, where you don't have to do renormalization, but you still get an observable that is manifestly positive. So its spectrum is like in the positive half line. So what this threshold does is basically what you get this probability distribution, which is like non-zero on the positive half line. And what you do is the probability to measure a particle is you integrate, instead of over the whole half line, you integrate from B to infinity. And that gives you the probability to have measured something. And the probability to not have measured something is you integrate from 0 to B. Essentially.
Yeah, okay, thank you. You can also think of this as like the variance like of the observable phi of Fi, right? Like in the sense of like it's in the vacuum at least, I guess.
Yeah.
But okay, cool. I'll think a little bit more about this, but thank you.
Okay. Are there further questions from the audience? There's one in the back there. Oops.
What do you think are the next steps now that you've actually violated the Bell state? What's the future of this for you?
Well, this is technically still ongoing, so we still need to fix some things, some more technical things in the background. After that, there are a couple of things one might want to look at. For example, quantum key distribution. We still have this polarization rotation lined up, where you really couple Procker to an electromagnetic field to rotate the polarization, and how to describe that. There are, of course, other things you could do. This is very inefficient. Maybe if you change how you couple them, if you try to tweak the detector model a little bit, you can get it to be more efficient. So these are some various things that might come next.
I think the last question before the coffee break.
Yeah, I think it's a quick one. So you consider particle and antiparticle, right? Could you have considered just a particle superposition of being here, not being there?
Sure.
Why did you consider the particle antiparticle explicitly? Was there any particular reason for that?
No, not particularly. I mean, you can do both. It was just that it was somewhat convenient for the amount of commutators you have to do.
Right. If there are no further questions from the audience, we are moving to a coffee break, I believe, for half an hour? No, 20 minutes? I should have looked on the schedule. Okay, 15 minutes, I've been told. So people in the audience back at home will see back in 15 minutes, and the people also here will remain seeing, but we'll see back here in this room in 15 minutes' time. Thank you. Okay, welcome back everyone. We're ready for the next talk, which is by Maté Farkas, also from the University of York, on Tyrolson's problem. Maté, take it away. The floor is yours.
Thank you, Dan, and all the organizers. So, disclaimer, I'm on the quantum information side of things, but I think at some point I mentioned to Patricia that I'm working on something, well, I'm trying to work on something a little bit related to quantum field theory, which is probably why she invited me very kindly. So this problem that I'm interested in, and what I'm going to talk about is none of it is my results, right? It's just something I really want to kind of get into, and one of the angles could be quantum field theory, although it's not a simple problem, I must warn you, but I'm hoping I might get some sort of insights maybe from quantum field theory. And the problem in a nutshell is maybe a little bit different from what many of the talks today might go into, which is that, again, I'm not sort of overly familiar with the QFT community, but a lot of what AQFT is doing is sort of trying to put a proper mathematical foundations to quantum field theories, but not necessarily expecting to reach different experimental predictions or different results from what we have seen before, let's say, in the lab. So at this point, as far as I understand, it's more about properly reproducing based on a solid mathematical foundation what we see in the lab, rather than sort of finding new physics, although that's very much a possibility, I presume. Now, this topic, Tyrolson's problem, is about a possible difference between the predictions of AQFT, basically, and the sort of vanilla non-relativistic quantum information, which is what I do normally. So, the setup in which this difference could happen is Bell non-locality, which we've heard about a little bit in the previous talks, but I will introduce it very briefly. So you can see I'm not an AQFT person, because for me time goes down instead of up, so I apologize for that, but these are the sort of drawings you would normally see in a quantum information talk about Bell non-locality. And the setup is pretty much what Christiane was describing to us, is that we have these two sort of distant labs who make some measurements on a shared quantum system. Right? And the key point is that these events, the measurements, are space-like separated. Now, to formalize this, we usually allow the parties to perform a one-off, some fixed finite amount of measurements. So here on this picture, like X and Y would be your possible measurement settings. And then, as we know, each measurement has like a possible set of outcomes. Often this set is infinite or continuous, but we will restrict to a finite set of possible outcomes. Right, so this is the experimental setup, right? This is what I described. Alice measures a property, we call it X, and she observes some outcome A. And similarly for Bob, there's a property Y, and the measurement yields an outcome that we will call B. And the important point is that these events, the measurements, are space-like separated. So you could actually put this on a space-time diagram, as we have seen in the previous talk. And what this really means is that what property Alice measures will not affect Bob's measurement outcome, and vice versa. Right, so this is our setup. This is an experiment that we can, in principle, conduct, and these have been done, right? And the original sort of key motivation for this is that you can observe some statistics. We will see that the object we're interested in is the measurement statistics. What's the probability that Alice observes A and Bob observes B if they chose to measure X and Y, right? This is your statistics. If you look at that, there are some statistics that you can explain using quantum physics, but you cannot explain using classical physics, which eventually led to the Nobel Prize in Physics in 2022, if you don't believe me that this is important. You can also explain it with non-physics, right? If you think about like superdeterminism and things like this. But if your main sort of competing theories are quantum physics and classical, let's say, Newtonian mechanics, one of them can explain some experiments, the other one cannot. This is kind of the main motivation behind Bell non-locality, but this is not really what I want to talk about here, rather a possible difference between, let's say, different types of quantum theory, basically relativistic and non-relativistic, if you want to sort of simplify things a bit. Now, the non-relativistic, which in this setting is often called the quantum spatial set of correlations. So the correlation is really just a measurement statistic, right? So when I say correlation, it refers to the probabilities with which you observe the outcomes. So usually we fix the number of possible inputs and outputs. And then we can, for a fixed number, we can define these sets of correlations. And the quantum spatial set, right, this is what the QS stands for, is a set of all the possible measurement statistics that you can get in a Bell experiment that has this description, right? This is nothing but the Born rule. The important bit is that the measurements of Alice and Bob live on some tensor product Hilbert space, right? So like your state lives on the tensor product Hilbert space, and then Alice locally measures on her Hilbert space, Bob locally measures on his Hilbert space. We can use just sort of normal quantum states. You can formulate this in a C-star algebraic setting. I chose not to do that here. The sets will be the same, right? So it doesn't really matter. But for me here, a quantum state is just a positive semi-definite operator with unit trace. But importantly, in this definition, it lives on a tensor product Hilbert space. And then these guys, the M's and the N's, these are the measurement operators. So they are, again, positive semi-definite operators on the local Hilbert spaces. And for each measurement setting, which is X for Alice, if you add up the measurements, add up these operators over the possible outcomes, which is A here, you get the identity operator on that Hilbert space. This is just to ensure that these give you valid probability distributions. So if you want like sort of the most general model of a quantum measurement in this setup, this is what you should use. Right, so quantum spatial correlations is a set of correlations that have a model like this. Okay? About the set, because it will be relevant, the set is convex, but it's not closed. Maybe you wonder about the use of the word but, because some of these two things are not really related, but you know, convex is nice, closed would be nice, it's not closed, but we can always close it, right? So that's our non-relativistic model for this Bell scenario. And well, what is the relativistic model, which in this context is often called the quantum commuting correlation set? It's the exact same thing, but now I don't have a tensor product. Right? I just have a product. Now, for this to work, okay, the state is the same, but I have only a single Hilbert space. The measurements are the same, but again, they live on a single Hilbert space, the same Hilbert space. But for this to sort of make sense, the measurement operators need to commute, right? And this is what you would probably end up with from a AQFT perspective as your model. So if you want to sort of really put it on some space-time, then eventually you would get something like this. You don't have a priori a tensor product structure to your Hilbert space. You have sort of a single measurement algebra on your whole space-time manifold. This set of correlations is both convex and closed, which is nice. Right, so these are our two potentially different models. Now, what's Tiriason's problem? Basically, fix the number of inputs, fix the number of outputs. The question is, what's the relation between these two sets? And now I close the quantum spatial set because it's easier. Obviously, they can't be the same as if one is closed and the other isn't. So I close this set. It doesn't really matter for the sake of experimental observations whether we're looking in a closed set or a not closed set. Now, one way is easy. Clearly, the quantum spatial set is included in the quantum commuting set because if I have a quantum spatial correlation, the tensor product one, I can take my big Hilbert space to be the tensor product Hilbert space. I can pick the operators of Alice to be the sort of original operator on the first Hilbert space and then identity on Bob's Hilbert space and vice versa, and these two will commute. Right, so one of them is included in the other. The question is whether the commuting set is more general than the tensor product set. Whether we could, in principle, if we take like the sort of base axioms of AQFT, could we see correlations in an experiment that do not have a tensor product explanation to them? And the reason why it's called Cyrilson's problem is that Cyrilson claimed that these two are the same in this paper without a proof. But then it turned out that he couldn't actually prove it if your Hilbert spaces were infinite dimensional, which is, the relevant case, usually, especially for AQFT. So it's here without a proof, and then later he sort of started thinking of it a bit more, and well, when he was pressed about this question, he realized he could prove it in finite dimensions, right? So finite dimension comes with a proof, but then he realized he couldn't use the same argument for the infinite dimensional case. So it's not that clear, but then this result actually has another implication, which is that when your input and output sets are essentially minimal, okay, 2 is the sort of first non-trivial amount of measurements and measurement outcomes you can have, then actually these two sets are also the same. So for this one case, the two sets are the same. And this is actually maybe instructive to see, like a proof sketch. So if both my input and output sets are the set 0, 1, so you see that the constraint on the measurement operators is that if I take measurement x, the two operators need to add up to identity. So to fully characterize the measurement, I don't need to specify both of these operators. I can just give you one of them, and the other one will be identity minus that one, right? So to describe a single measurement, one operator is enough, and this operator can also be projective, which is due to Naimark dilation. You can always sort of enlarge your Hilbert space so that your operator is actually a projection on the bigger Hilbert space, right? So every measurement, if it has two possible outcomes, is described by a single projection, which means that if, say, Alice has two measurements, to fully characterize those, I need to give you two projections, and the same for Bob. What this means, in other terms, is that the measurements of Alice and also the measurements of Bob, they are representations of the universal C-star algebra generated by two projections. If you don't know what that means, it doesn't really matter. You can define, I think Chris told us about star algebras. You can add some more structure onto those and you get a C-star algebra. Any sort of specific operator that satisfies the generating relations is a representation of this algebra. And in this case, it's just an algebra generated by two projections, right? I don't have any more relations. If I want to specify Alice's measurements, let's say, I need to give you two projections. Any two projections is a representation of this universal C-star algebra. And now we can use some of the knowledge about these objects one of which is that the irreducible representations of this algebra are either one-dimensional or two-dimensional. There's probably kind of a contest here of like what's the earliest thing you can cite for this result. I could only go back to 1941. In some of the quantum info community, this is referred to as Jordan's lemma. That's like, if you search for that, good luck finding it. You can definitely find it in this paper, which I think is, it goes by two projections in general position. But what this means is that, morally speaking, you can get away with just having your measurement operators being one-dimensional, which is trivial, right, or one-by-one matrix, or two-dimensional, which is a qubit, right? And the sort of actual consequence of this is that the extremal points of our quantum commuting set, which exists because it's a convex set, they can be realized in finite-dimensional Hilbert spaces, basically two-dimensional. And that also means that all of the points inside the set can also be realized by a finite-dimensional Hilbert space, which means that point 1 kicks in. We are in a finite-dimensional setting, and the two sets are the same. So this is good, but it doesn't solve the problem, right? It only solves the problem in this very specific and sort of smallest scenario. If I increase any of these, probably, at least, I mean, you probably need to increase something on Alice's side and something on Bob's side, but if you increase the number of settings or outcomes by just one, we already don't have this result. We don't have sort of nice things to say about the corresponding algebra. Now, there has been a resolution of the problem. In general, it has been shown that the two sets are not the same, which was maybe a bit of a surprise in 2020. Okay, this was sort of semi-published in 21. I think it's still not fully published, but I think people believe this is true, that these two sets are not the same. And this is a consequence of this paper, which has this very cryptic title, MIP star equals RE. This is sort of a computer science lingo. Maybe they are listening. But essentially what this means, the left-hand side is essentially referring to this set, the quantum spatial set, the tensor product correlations. The right-hand side refers to a complexity class of computational tasks. And this class is really, really complex. It's undecidable. And essentially what this means, well, one of the consequences of this result is that the quantum spatial set is incredibly complex. It's very difficult to describe it. If I give you a random correlation and ask you, is it in this set or not, even with some error, it's an undecidable problem. And why does this mean that the two sets are different? Well, because we have efficient, okay, this is probably not efficient, but we have computable algorithms to approximate this set from the inside, which is just take a Hilbert space and another one, tensor them together, search for everything, increase the dimension, and continue, right? So you can brute force this set from the inside. Okay, it's not efficient, right? But it's an algorithm. And we have, again, not necessarily efficient, but we have some outer approximation algorithms for the quantum commuting set, which is what is known as the NPA hierarchy of semi-definite programs. The bottom line really is just that we can compute some approximation from the inside to CQS and outside to CQC. If they were the same, we would have an algorithm that could decide whether a point is in CQS or not. But we cannot, which is a consequence of this paper, therefore the two sets cannot be the same. This is essentially the argument of this paper. I mean, they do spend most of their time proving this thing, but the consequence can be summarized as such, which is great. I mean, it's a breakthrough result. It was a big surprise. What bothers me and a lot of other people, presumably, is that the construction that they can extract from this for a point which is in the commuting set but not the spatial set is not really a construction. They give you an algorithm of how to generate such a point, which is classic computer scientist behavior. They give you an algorithm, but you can't write this down. You can't feasibly churn it through. They say, well, the number of inputs and outputs that would be required for such an example is there's no reason to believe that it's infinitely many, and probably 10 to the power 20 is enough, which is not very helpful, right? So what I'm interested in is where to find some explicit constructions that are in the commuting set but not in the tensor product set. And one potential avenue would be algebraic quantum field theory, right? Because this is somehow it's the natural language for describing these commuting correlations, right? Because as we've seen in the previous talks, in AQFT, space-like separated regions correspond to some commuting C-star subalgebras of some big observable algebra. Right? I probably don't really need to repeat that. So AQFT provides like a natural framework to look for such correlations because the constructions are by design in this commuting paradigm. There's of course problems. One is that I don't know much about algebraic quantum field theory. This is a personal problem, but a broader problem is that you need really wild quantum field theories to even hope to find these sort of counterexamples. And one of the things, not the only thing, but one of the things that you would need to find a counterexample, an example in the commuting set but not in the tensor product set, is that you need a quantum field theory which doesn't have the so-called split property, which would sort of enforce that you can always represent your correlations on a tensor product Hilbert space. And as far as I'm aware, algebraic quantum field theorists like the split property, and any sort of physically conceivable theory that can be described in AQFT, which I'm not sure if there's that many of them, but all of them have the split property, and it's considered somewhat unphysical not to have it. So if you want to find a counterexample through this route, you should look into QFT without the split property, which is a bit wild, as far as I'm aware. But we might get some sort of intuition from this direction. Any questions, Benito?
When we get to the questions.
Yeah, there will be questions on this later. I only have one more slide, which is not about AQFT, but this sort of other route, which might be a bit more tractable, but it detaches from physics, which I personally like, but doesn't necessarily mean that I can solve this. But another avenue of finding these sort of examples would be a more sort of purely algebraic route, which is what I call representations of measurement algebras. So now if I have a measurement with m outcomes, so I have my sort of measurement operators here, these are the guys that add up to identity, I can define these observables. Okay, I cite this paper. This is not where the observables are defined first, but I think this is an excellent paper if you want to look at the history of Sirelson's problem and some of the relevant maths. Of course, this was published before Sirelson's problem was resolved, but I think this is still a great resource in general. You can define these observables, which is essentially you take the discrete Fourier transform of your measurement operators. If your measurement operators are projections, which they can be, as we've seen before, then this operator is a unitary, and its mth power is the identity. Which sounds nice, right? This basically just means an m outcome measurement is a representation of Zm, the integers modulo m, as a group, right? Because it has a single generator whose mth power is the identity. A bit more generally, if you want to put it, if you want to think about sort of the whole operator algebra, then any M outcome measurement is a representation of the group C star algebra of that group, which is a thing. It's again like a sort of universal algebra. And now if we have more than one measurement for Alice, let's say, which is always the case, then the relevant object becomes the free product of the group, right? If I take a measurement operator from one measurement and another one, they don't necessarily commute. So any sort of word I can write down as a product of these is a different element. This is what a free product really is. And then the relevant object becomes this C star algebra, the group algebra of the free product of sort of the two groups, right? So if I have an M outcome measurement and an N outcome measurement on the same side, then the measurements are representations of this C star algebra. So these are the places to sort of look at. And then even in the sort of smallest case, so we've seen if both of these are 2, if I have 2 measurements with 2 outcomes, nothing interesting happens. If I have one measurement with 2 outcomes and another measurement with 3 outcomes, this could already be interesting, right? You could already, in principle, find an example which is not a tensor product correlation. There's nothing telling us this can't be done. And this is a group that is very well studied. This is what's called the modular group. So there's extensive literature on the representation theory of this group. I don't think it's sort of fully solved, but there's places to look. And then, of course, you can look at other scenarios, different M's, different N's, and try to work out the representation theory of these things. And that was my last slide with actual content. I leave the summary up for your viewing. Thank you.
Are there questions from the audience? I see one there from Chris.
Thank you very much, Maté. So this is about the split property. And as you said, in AQFT, there is the split property, which typically works when there is a little safety margin. If you have 2 regions that are not only space-like separated, but space-like separated with a gap, that's when you would expect this tensor product representation. But another thing you could look at is where you have regions that just touch at the edge. And there you would not have this splitting, or at least that's not what the split property says. And moreover, that is the setting where Summers and Werner looked when they wanted to show that you have maximal Bell violation in the vacuum state. So it could be that you don't totally have to go to wild theories, but you might have to look in that touching set. That's a comment, and I don't know if you have a reaction.
Yeah, I do. Thank you. I think that's a very good point. Maybe the one downside of this could be if you want to actually test this, which is maybe not something I emphasize really. I guess one of the long-term consequences of this would be that you could in principle test which description of nature is the proper one. If your space-time regions are touching, that's probably not something you can experimentally test. But of course, we're very, very far away from that. So yes, that is a very welcome comment. And we might just also add something very briefly to that. You can also potentially observe this difference in what's called a contextuality scenario, where you don't really have 2 space-like separated regions. You have to add in some extra assumptions which might be difficult to justify, but on paper they work, and you could in principle see this difference there as well. So yeah, there are some potential ways that you can go around it that doesn't include the split property. Thank you.
Yeah, let me just add to this a little bit, right? Because if you go back to your definition of the CQC set, right? Mm-hmm. There's nothing there explicit about space-like separation, right, mathematically, right? So it's, in principle, you could just look at one given algebra and 2 different subalgebras of this larger algebra and just ask these questions, right? But it's true that usually when people mention bionic inequalities, they want to talk about space-like separation, but in the end, what you really need is to have these commuting subalgebras, and then you wouldn't even need to think of the observers as being attached to regions, but just having access to independent degrees of freedom in the sense that the measurements that they can perform commute. Right?
Yeah.
Just adding to the
Yes.
to this.
Yes, thank you. That's very true, right? So as long as you can justify your commutation relations, you're good. And of course, again, on paper, you don't even need to justify it.
Could I also ask a question? I'll just use my my chairing privileges. What about commutative C-star algebras? Because, I mean, there essentially everything commutes, so you have a lot of operators to test this this CQC and versus CQS on. I mean,
Yes.
you could even. I could imagine that this might be the same for separable, if you can do things on separable Hilbert spaces, but you can do Van Neumann algebras on all kinds of wild, sort of infinite dimensional Hilbert spaces, things like this, where, I don't know, it might also be an interesting avenue, which...
So what I'm thinking is, if Alice's measurements, say, commute within each other, you will land in the classical set of correlations. So you won't even get out of there, and then the two will be the same.
I see. Okay.
That's what I believe, at least. Yeah.
Thank you.
So when you mentioned this complexity theory result, you're a bit vague or weaselly about whether it's been proven or not. What is the kind of status of that, or why were you not willing to say that it's proven?
Mainly because, as far as I'm aware, it's not like published. There's been like sort of pre-publication shortly after it was announced. After that, there was a sort of mistake spotted, but that's been fixed. And like, I mean, a lot of people have dedicated a lot of time trying to understand the proof. It's very long, right? This paper, I'm not sure if you've seen it, it's like 180 pages of mainly computer sciencey things that are very difficult to penetrate. But my understanding is that the community has accepted it, just not the journal. I don't know. I don't know why, but yeah.
Okay. With that, we thank Maté again. And we move on to our next speaker.
Yeah, the potential barrier. Ok, bla bla bla. ¿Y está prendido? Okay.
Okay. So our next speaker is Benito Juárez-Aubry, also from the University of York. Semi-classical gravity. Why and how? Please, Benito, the floor is yours.
Okay, thank you, Dan. Yeah, thanks so much, Patricia, Filippo, and Christiane, for the very kind invitation, and Rick also for the help with organizing. It's a pleasure to be here in York, as every day. So let me, change gears a little bit with respect to the previous talk. And I want to talk about semi-classical gravity, which is something that I've been interested in for the past few years. And then the subtitle is Why and How. And the reason why those two questions are there is because you will see in the how it's kind of hard to do it. And so then you might really wonder, well, why go through all the trouble? So hopefully in the why there will be enough motivation for you to see that this is interesting. Okay, so outline. So the why, which is the motivation, the how, which is what we are doing now with some collaborators like Stefano, Patricia, and others, Daan as well. So that's in the current work, and then just some outlook. Okay, so this is kind of RQI circuit. So my motivation is to be RQI driven. So first of all, what is RQI? It's a tough question. So RQI is a discipline. Okay, so there's some sociology there, and it studies quantum information. So things like communication, energy, entanglement, entropy, measurements, equilibrium, thermodynamics, etc. In a relativistic context. So in situations where, the speed of light is constant at least, and maybe there is some gravity. Okay? So in practice, what this means is trying to generalize or understand concepts of quantum information in the QFT setting. In practice, this is very much of what is done in RQI. Okay? So for example, just a very classic example of quantum field theory, the notion of an equilibrium state is phrased as the KMS condition in quantum field theory, okay? So in RQI, you work with the KMS condition operationally when you refer to equilibrium states. And then, of course, you have all these other, so that's a very classical example, but you have all these other things which are more modern and maybe more interesting, more state-of-the-art, such as, entanglement entropies, relative entropies, measurement schemes, etc., and a lot of interesting things that are going on today. So, indeed, the arena of RQI is often quantum field theory in curved spacetimes, sometimes also a little bit of algebraic quantum field theory. So, indeed, when I was doing my PhD, I did it in what would now be called RQI, but back when I was doing my PhD, people asked me, what are you doing? I said QFT in curved spacetime. So the terminology has kind of changed. Okay, so interestingly, arguably the most famous paper in quantum field theory in curved spacetime is Hawking's particle creation by black holes paper in the 70s. And indeed, it really sits at the intersection of quantum field theory and quantum information. And just to reflect on it, I wonder if this would be called an RQI paper today. So this is the very paper that gave rise to this information loss puzzle, okay? And so the key idea there is that if you consider quantum field theory in curved spacetime, and the spacetime has a collapsing star forming a black hole, you get, when you compute the output of radiation and what happens near the horizon, you get this information that the quantum field gets stimulated in such a way that it radiates away Hawking radiation, which is thermal at Hawking's temperature. And this eventually, through some back reaction arguments, leads to black hole evaporation. And once this evaporation is completed, the information inside the black hole is lost. And this sort of, the standard way of saying this is that this contradicts unitarity in quantum theory, or predictability more generally. Okay, so tons of papers have been written on the topic, and even I have written one. And so I will tell you what I wrote and why this is part of my my motivation for studying semi-classical gravity. Okay. So this is the picture of black hole evaporation that famously appeared in Hawking's paper in the 70s. Okay. And as you can see, what would happen here if you really, so this is a semi-classical picture of the evaporation, okay? And if you really had evolution equations for semi-classical gravity, that is, equations in which quantum matter sources the Einstein equations and the quantum matter behaves according to the dynamics in the spacetime that they curve, okay? What would happen is that you would prescribe some initial data for the state and the gravitational configuration, so the metric and extrinsic curvature or something like that, down here, okay, in a putative Cauchy surface, and then the system would evolve all the way to there, and then according to information loss puzzle, according to the paradigm, let's say, of Hawking, what would happen is that this would lead to the evaporation entire evaporation of the black hole, and then there would be a post-evaporation region that I have indicated there with these red dots, where essentially you would have flat space-time again, and the state would look just like a thermal state with no information, even if you started with a pure state. At late times it would look mixed, okay? So I think, so this is a kind of way of saying this with words, but it's been pointed out already for some years by people like Andrew and Wald that this is not entirely surprising, because if you look at Scry plus, that's not a Cauchy surface, so you can't really hope that the state would remain pure on Scry plus if you start with a pure state on Scry minus. Okay? So what I've written about concerning this puzzle is in this paper in 2024. Well, I said that actually one shouldn't really believe this diagram, because we have a lot of experience and a lot of examples, both classically and in quantum field theory, which indicate that Cauchy horizons are unstable. So in particular, there in the region where you have this lower edge, is that what it's called in English, of a triangle, like in this region, that's a Cauchy horizon right there. And then you would, and of course it emanates from this singular evaporation point, which is not really a point in the manifold. And so one would expect that at this Cauchy horizon, there is the development of some instability, okay? So people like Christiane Klein, who is with us, has studied in particular this situation in Kerr de Sitter, I believe, if I'm correct. And other people have also studied this situation in various contexts, in instability in quantum field theory near Cauchy horizons. Okay, so anyway, so in general what goes wrong is that the Hadamard condition breaks down. I haven't told you what the Hadamard condition is, but I will. And so stress energy tensor blows up typically. Okay, so let's see. So this is so of course, in order to understand all of this picture, you need to have a good understanding of semi-classical gravity, which we don't actually. So we just say words and stuff about information loss puzzle, and this is why there are so many papers written about it, because nobody really knows how to solve the equations. But if you wanted to really understand the puzzle rigorously, and the absence of a puzzle, for example, by instability of Cauchy horizons, you would need to understand semi-classical gravity completely in a mathematical way. So this is, I think, a good motivation from the RQI point of view of why you would like to understand semi-classical gravity. Okay, at least it would help you solve an interesting RQI puzzle. Okay, so the question is, how do quantum fields affect the space-time geometry? And of course, you need quantum gravity for that, but in some approximation, in some regime, you would like semi-classical gravity to tell you something about it. And indeed, historically, a lot of our understanding of quantum gravity comes from semi-classical analysis. This is why people make connections between gravity and thermodynamics, blah, 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 okay, because of semi-classical arguments. And of course, good examples where this is relevant is black holes, cosmology, and there are these important questions like black hole evaporation that I just mentioned. But there's huge room for improvement in our mathematical understanding. So in particular, we don't even know local well-postedness of semi-classical gravity. We don't know what's the regime of applicability of the theory, and we still don't know what's the interplay between semi-classical gravity and measurements, okay? So these are at least three very interesting questions that I think is worth exploring. So let me tell you what the theory is, and in order to do this, I'll just consider that, you know, I was educated as a person in quantum field theory in curved spacetime, so quantum field theory for me means like take a free scalar field, it's already too complicated like that, okay? So we'll consider free Klein-Gordon field as a Maté model, okay? So there's no more, standard model is not there, whatever. This is just to get a model that is simple enough. And you're interested in studying the system of equations 1 and 2, which is a coupled system, okay? And what you have is on the left-hand side, you have the Einstein equations, possibly with a cosmological constant, and they are sourced by the expectation value of the renormalized stress energy tensor of the Klein-Gordon field in a suitable state. So what is the dynamics of the quantum side of the what is the dynamics of the quantum field? Well, you want to characterize them in terms of the two-point function of the Klein-Gordon field, which entirely characterizes the state, at least if you're in a quasi-free state. Okay, and this ought to be a bisolution to the Klein-Gordon equation, where the differential operator defining the equation, so the Klein-Gordon operator, is the one corresponding to the metric that is a solution of equation 1. Okay, so a fact of life that makes this very, very hard to study is that the right-hand side of equation 1 entails renormalization, because this is not a linear observable in Klein-Gordon theory. And there are many sophisticated ways of talking about renormalization, and indeed sometimes one really does need to do it in a sophisticated way. But the simplest way of understanding it is by the old point splitting, which was advocated back in already 78 by Wald and so on. Okay, so how do you define this stress tensor? Well, assume for a moment that we're in a fixed space-time, which is smooth. It has all the nice properties that you want, globally hyperbolic, whatever. And you want to define the unsmeared stress tensor in a Hadamard state. And I will say in a minute what a Hadamard state is. Okay, so what do? You notice that the two-point function has a certain singular structure, and the singular structure of the two-point function is what will make it Hadamard. Okay? What is that singular structure? Well, you know that it depends entirely on the geometry and the parameters like mass and curvature coupling of the Klein-Gordon equation. And it is precisely characterized, the singular structure, by something called the Hadamard parametrics. This is why they are called Hadamard states. So all Hadamard states have a singular structure in terms of the Hadamard parametrics, which is as follows. Okay, so Hadamard parametric is a bidistribution. Okay, and it's a solution of the Klein-Gordon equation up to smooth terms. Okay, and it has certain distributional singularities that are placed in a very specific way. So you have this delta, which is the Van Vleck-Moret determinant. I'm still good with time, yeah? Okay. Delta is the Van Vleck-Moret determinant, so it's purely geometric object. It's smooth and finite on the diagonal. The diagonal goes to 1. And you have these V coefficients that are obtained formally by certain transport equations called the Hadamard recursion relations, which ensure that the Hadamard parametric is a bisolution up to smoothing of the Klein-Gordon equation. And then this sigma is 1/2 of the squared geodesic distance between these 2 points. This epsilon indicates that there's a regulator there to characterize precisely the distributional singularities of this thing. But the interesting thing is that sigma there, because it is geodesic distance squared, you know that geodesic distance between 2 points vanishes when the 2 points are connected via a null geodesic. So for any pairs of points that are connected by a null geodesic, you are in the singular support of this bidistribution. If you're a Hadamard state, that's exactly where your singularities are also located. So this difference makes this finite. And in particular, if you're Hadamard, it makes it smooth. Okay? So this difference is a smooth bisolution of the Klein-Gordon equation up to smooth term. Okay? Right. So what do you do to define the stress energy tensor? You apply an operator to that difference, which is essentially a point-splitted version of the stress. It comes from a point-splitted version of the stress tensor. So if you think of the classical stress tensor, you would insert a classical field there and there and there and there. And there you would put 2 copies, take the limit, and that would give you the classical stress tensor. So this is exactly what you do, but you don't put the classical fields, you put this bidistribution there. Okay? And when you do this, then you take the limit, and you want to define that as the stress tensor. Now there's a subtlety. So in order to really get conservation, because this is not really a solution to the Klein-Gordon equation, so in order to really get conservation, you need to add another term which is connected with the coefficients of these, to these Hadamard coefficients here. And then you additionally have some renormalization ambiguities, because you need to also introduce a scale to the to the problem to have this logarithm be dimensionless. Okay, so that's very technical, but what I want you to take away is that these terms like V1 and this theta, which you really shouldn't get rid of when you talk about this renormalized stress energy tensor, are higher order terms in the metric. Okay, so they go like box R, and they have like box Ricci tensor, and two derivatives of the Ricci tensor. So when you put it on the right, when you put this on the right-hand side of the equations, they really no longer look like a second-order equation that you can render into a quasi-linear hyperbolic form, but they've really become a fourth-order system of equations, okay? Where this IAB and this JAB contain these higher curvature terms, and this V1 is the one, as before, that I mentioned to get stress energy conservation. So the system that you end up really wanting to solve is the system which looks like 3A, in which you have the quantum aspects of the equation encoded in this two-point function and in this renormalization procedure, and the rest is a kind of fourth-order classical problem. Okay, so if you wanted to view this as an initial value problem, you would need fourth-order initial data on an initial surface, and you would have, as initial data for these bidistributions, you would have the correlation functions for the surface canonical commutation relation generators, so the momentum and the field. Okay. So okay, so this is what you a priori think you need to solve, and okay. So I mean, this is a very kind of complicated problem to solve. So you first want to study some simpler models. So here's a simpler model that we studied. This is kind of a semi-classical version of a Yukawa scalar system, in which one is classical, and it appears here in red, and the other one is quantum. And you've sourced by the expectation value of phi squared, so there's still some renormalization to do. Okay? So the first thing that you notice is defining what a Hadamard state is in the first place requires knowledge of psi and all its derivatives, because you actually need to know this exactly in order to be able to say where the singular, what the singular structure of this is. And that's a problem, because on the initial surface you only know psi and psi dot, which is all the data you have. In order to obtain psi triple dot, you would need to use the equation, you only know psi and psi dot, and in order to use psi double dot, you would need to take a derivative of the equation on the surface, and so on and so forth, in order to obtain all time derivatives of psi on the initial surface, and to be able to give the definition of a state that is closer and closer to being fully Hadamard. Okay. So you can see that there's a little bit of a problem even on defining the initial data. But overall, knowing the regularity of the state to higher and higher order, so to approximate Hadamard to higher and higher order, requires controlling derivatives of the field equation on the initial surface and more of those equations. Okay, so in principle, a Hadamard state requires controlling an infinite tower of initial data conditions. And actually, we formalized this observation in a 2022 paper with Bernard and some collaborators in Mexico City. And we call it surface Hadamard initial data for semi-classical gravity. If you don't have that infinite tower and you just have, let's say, k of those, then you get an adiabatic, what's called an adiabatic state. So it's close to Hadamard, but not quite. But that's good enough. Okay? And there are also some other subtleties in semi-classical gravity, because you don't even have geodesic distance on the surface. In the Hadamard condition, it's a covariant condition, so you have geodesic distance in space-time. Okay? So this scalar model can actually be solved perturbatively to arbitrary order, and we've done that in that paper. So what truly is the free initial data of semi-classical gravity? So one could say, well, forget about defining all those complicated distributions. When I take the limit in the definition of stress tensor and all renormalized observables, I'm only interested in the smooth part of the Weidmann function, of the two-point function. So I could just prescribe 4, let's say, smooth or CK pieces of data. However, these data cannot be propagated because the smooth piece doesn't obey the wave equation. It obeys it up to smooth terms. So you would still need to construct the distributional singularities of the data by the method that we have mentioned before. And you would still need to verify that positivity holds, and these are not F, but these are really the full correlations. Okay, so to satisfy positivity for the state, otherwise you don't have a state. Okay. Okay, and then I make some comment about one really wants to work with data in a Sobolev space, but you don't care about that for now. Okay. So beyond the former, also in the structure of the theory, one has constraints and gauge. The constraints are the usual Gauss and Hamilton constraints that appear in GR. And the gauge can be fixed even for this fourth order system if you ignore the stress energy tensor on the right hand side in such a way that you obtain a quasi-linear second order hyperbolic system. So you basically take a fourth order system and you render it in second order by introducing additional variables, and then you do some magic with the good gauge choice and it becomes very nice. So that gauge aspect is not very scary, contrary to what some of my collaborators think. Okay, of course, what's complicated in equation 8, 9, and 10 is that the form of these equations looks nice, but of course these B's are. So let me just tell you what we are doing now. So we're currently studying with Stefano the local well-posedness of, so now I don't want to get perturbative solutions to a kind of Yukawa model, but I want to get exact, I want to prove exact existence and uniqueness of solutions here. And moreover, now it's nonlinear, so it's a phi to the fourth problem. So this means that you have to do in addition, not just solve a linear problem, but you need to solve a tower of linear problems and do Picard iteration, okay? And we are very much close, I think, to, we are well advanced in our understanding of this problem. Another thing that we are doing is trying to understand the linearized problem, and this is something that we are doing with Mark Bradshaw. So Stefano and some collaborators like Nicola Pinamonti, etc., have a very nice paper on linear stability of semiclassical, or instability of semiclassical gravity near Minkowski spacetime, but they reformulate the initial value problem as a forcing problem instead of a Cauchy problem, which is something that you can do for linear problems, but with nonlinear cases it's less clear. And with Mark, we are trying to understand this, but with a version where you don't reformulate as a forcing problem, but maybe really try to do this in terms of data. And yeah, maybe this is connected with regime of validity of the theory and so on. And then another question that we are studying with, mainly with Daan and Patricia, but also under the huge influence of Kasia and Chris that give us advice and so on, is what happens with measurements in the situation in which you have the FV scheme, but the coupling region is dynamically generated by fields, right? And so so the complex coupling is produced by apparatus coupling fields, okay? So Dan likes to think this in terms of quantum reference frames and so on. And somehow, if you don't do this with dynamically generated coupling, you can see that throughout the measurement scheme, you have violations of stress energy. So you really need to understand this, how stress energy is conserved throughout across measurements with dynamically generated coupling. And this will, hopefully, we can then bring this to the semi-classical gravity regime as well to understand measurements there. So let me just, I think probably my time is nearly up, but let me just thank you and then give you two invitations. So here in York, we will have the new directions in semi-classical gravity workshop on the week of the 14th of September. In principle, registration is closed, but do reach out if you really want to come. And if you're a local, of course, you know, tell us informally as well. And we also run the semi-classical online network exchange virtual seminar called SCONE. And we have 2 series every year, and the next one starts in September and it runs to December with 1 talk every year, normally in the first Monday of the month at 4 p.m. And you can actually register for the mailing list to get an announcement of our SCONE seminar. So that's, yeah. 2026? 2026, sorry. Yes, I'm just, yeah, thinking too much in advance. Okay.
audience? If not, okay, yeah.
So regarding the specific coupling of the 5^4 with the scalar quantum field, right? I assume that there's progress that we'll hear perhaps more about soon, as you said, but how likely would you say that it would be to be able to generalize these kinds of procedures to slightly different nonlinearities of the or couplings even between the field psi and phi, or complicate things a little bit further in the sense? Okay. How specific is the theory and the development you have to this model, as opposed to something a little bit trickier?
So in our current way of approaching this problem, it's very, very model specific. So we are really using that we are in Minkowski space-time. So we are using Fourier transforms and estimating things with the help of Fourier transforms, for example. And we are also, we've kind of reformulated the way in which we do the renormalization also to do it. Because, of course, the problem is that you don't, so remember, the problem is that you don't know what it means to be Hadamard because you don't know these functions here, right? So what we've done is that we've reformulated this problem by getting a fiducial Hadamard state which only obeys equations like that, and then introducing this as a perturbation in perturbative algebraic quantum field theory to calculate this in the using Bogolyubov map or quantum Muller map to introduce that as a perturbation. But you get this as a perturbation series, but we know that it converges by perturbative agreement of Hollands and Walsh. But all the estimates that we do also on this convergence series, because you need to estimate this in a certain norm, and we are also using very much problem-specific techniques. But you know, this is the way you start. I mean, there's no other way of doing this. You need to go little by little.
Thank you.
Do you want to add something?
Maybe just since you said about more general settings, probably the fact that it is phi to the 4 or psi to the 4, according to this notation, it's not really restrictive. As long as it is polynomial, I think everything can be done.
That's probably true, yeah.
What if it was polynomial on the derivatives, for instance, or something like that?
If there are some derivatives, it's usually a bit more careful. One should be a bit more careful on what to say. So I don't have a certain answer, but maybe something can be said anyway. Probably you need to require a bit more regularity. I don't know, but one should be more careful. Yes.
What if the interaction is on the phi derivatives, like nabla phi squared coupled to psi?
If the interaction is here, like in gravity, you mean, or?
No, I mean like
the interaction. Which interaction?
Because you have the coupling between the two, which is like a Yukawa thing, right?
Yeah.
So yes. The quadratic term of the Yukawa thing, what if we replace that by derivatives?
Ah, yeah, okay. I think this is what you were answering.
So you mean some derivatives in the phi square?
So the coupling is like a psi squared phi, right?
Yeah, exactly. The classical counterpart is
the psi squared by nabla psi squared phi. Could you do something like this?
But then this would change this equation as well, probably.
Yes.
Okay, we can discuss more later.
Yes. I think the problem is the same with derivatives. It's a bit more.
Okay, I think it is time for lunch for us, because otherwise we might be run out of fish and chips. So we want to thank Benito again for his talk. And we are back here at 2, and I believe Patricia. Okay, so we are back here at 2.
Okay, so welcome back. I hope you all had a nice lunch break. We did. And the first speaker is again Chris Fewster here from York, and he will do a little talk about career development in York. Yes.
Okay, thank you. Hello again. So as advertised, this is the slot about career development at York. So without further ado, this is somewhat structured on the who, what, where and how model. So in terms of the who, I've put up some of the our colleagues here who are interested in aspects of relativistic quantum information theory. So we have 5 faculty who would, broadly speaking, count under that label. And then we have further guilty parties listed here, our current postdocs, who you know, 2 of them are organizers. Benito has spoken, Stefano is chairing right now, and Daan was chairing in the morning and will speak later on. So this is the team, plus at least 5 current PhD students working in quantum information. It's difficult to count because they keep moving around. But we have 5 or so at the moment, and there are going to be 2 or 3 more who will join this September. Also difficult to count, it turns out. Okay, so that's the who. The what, we have pretty wide interests across that group of people, but in general, I think the center of mass, you could say, lies in the mathematical quantum field theory end of relativistic quantum information. You already heard my talk and Christiane's talk, you will hear Daan's. This is sort of the center of mass of where we are. You will also hear Kasia's talk later on. So among the things we study, the theory of measurement for quantum fields, quantum reference frames, which I think Daan might talk about at some point, Unruh detectors, of course, which lots of people like, and Atsushi has written a very influential review on with colleagues. Entanglement in quantum field theory in curved space-time, that's particularly Patricia. Semi-classical quantum gravity, we've already heard from Benito. Edge and boundary effects in quantum field theory, that's a recent interest of ours. Bell inequalities you've heard of. And then there are other things we do because we, broadly speaking, came into this from quantum field theory in curved space-time, importing a load of techniques from there. And so our other business, as it were, would be things like perturbative versions of algebraic quantum field theory, or just the vanilla version of algebraic quantum field theory, and also the theory of Hadamard states, where, for example, Bernard Kay was one of the first people to actually nail down what a Hadamard state actually was, which actually turns out to be harder than you might think, and some of the nails keep popping up. But nonetheless, very influential in the field. In terms of the where, I've stolen some shots from the University of York site, so you can see clearly that York is a historic city with people in it. And so this is the sort of place, it is actually quite a nice place to live and work, and that is not just me saying it. I've been here long enough that I've probably forgotten what anywhere else is like, but people who have come here as students and postdocs seem to like it very much, and colleagues. In terms of where we are, we work in and are currently speaking from this building here, which we are on the East Campus of the university. This was formerly the computer science department, and there have been some improvements because it now not only says computer science, it says mathematics, and somewhere else mathematics is on top and computer science is down below. So this is the building we are. It's actually quite a nice building to work in because even though it is punishingly hot outside, actually it is not too bad in here at the moment. There's general agreement in the room. Where it is, the East Campus actually blends into countryside, and we have a lake. So it is actually a nice environment in which to work. Again, our building is just about visible. It's this one here, I think. Okay, so that's enough of the publicity shots. What actually goes on? Well, many of the usual things. We do have seminar series, not only in mathematical physics, but also in quantum information theory. And then there are several other relevant seminar series. For example, there's a version of the mathematical physics which is much more oriented to geometry, or as the geometers think of it, it's a geometry seminar with slight inclinations towards mathematical physics. But anyway, so that is, and there are others in algebra and number theory and so on. Something that is getting off the ground now is an early career forum, which is again angled at the PhDs and postdocs and early career lecturers among us. So that is a newish development. Maté is leading that, in fact. We also have been fortunate to maintain quite a strong research environment and culture, and this is now supported by specific funding for research culture through the university. I must admit that when I first heard about it, I thought research culture was something you find in the bottom of a Petri dish. But actually, it turns out that it is, by and large, something you can eat, because most of the funding seems to have gone towards catering, as, for example, supporting the catering today. But there are other things that it does, and it's supporting various students to do various tasks during the summer. So among the things that it also supports are sessions on, for example, writing grants or information about where to look for grants, our Research Away Day in the department, and so on. So there is a lot going on. Of course, within the department, we maintain funding for conference travel. This would have previously been a bit of a commonplace, but I think because there have been financial pressures, it is actually a little bit more of a distinction to say that we have hung on to that because we value the ability to travel for research and to do things like organize conferences. So some of the funding comes from the Departmental Research Committee budget, which, as it happens, I control. But actually somebody else approved it on my behalf because it was too close. One of the things we do, if people come here either as PhD students or as postdocs, is also offer opportunities for teaching. And for PhD students, this is typically in the form of teaching undergraduate seminars on the same basis, actually, as permanent staff teach them. Okay, so you do exactly the same job as we do if we're teaching a seminar. For postdocs and fellows, we try to make opportunities for some lecturing, and where possible, we try to make sure that that is an advanced topic in line with the research interests. Doesn't always work, and Christiane got some first-year calculus, but other people have had, for example, fourth-year relativity and other quantum mechanics. Daan's been doing third-year quantum mechanics, for example. This is an opportunity. It is not enforced, but it is, of course, something that people value because thinking about CVs and so on for the next stage, it is valuable to have teaching experience. We do have training courses, and some are mandatory. For example, there's a certain amount of mandatory training in order to take on any teaching, but then there are others beyond that that people can choose to do. We also do outreach various ways to schools. Some of our postdocs have been active in that. Pint of Science, which happens in pubs, unsurprisingly, and the York Festival of Ideas, which is an annual collection of many, many events, including talks and exhibitions and other things. And at least 3 of us have been involved in that over the years, giving talks or other events. So that's a lot. That's a small amount of what goes on. Of course, beside the research, which it goes without saying is excellent. Okay, actually I just said it, so it didn't, but anyway. So how do you get involved in this? So the how phase. So I'm going to divide that into PhDs and postdocs. So this is mostly for people watching online and also particularly for people overseas, because the system is different than you would be used to, perhaps. So applications are only through an online system. That's the only way we'll be able to consider an application. But always feel free to get in touch with us and have a chat about what sort of things we do. Applications are, through the online system, open all year round, but if you actually want some money to go with your PhD place, which most people do, then that actually places a bit of a constraint on you should apply by mid-January, really, in order to be considered when we're making the decisions about funding. Those decisions and the interviews that go before them, they all happen in February, more or less, and we make decisions in March. We often get inquiries around this time of year. I've just finished my master's. Can I start doing a PhD in September? And we have to say, well, sorry, there is no money to support that at this point. We do have some studentships. We do have some of those that can be used to support overseas students, but it is all quite limited, it should be said. So my advice is that you should be thinking of a plan B of alternative funding or alternative places where you are applying. And the website, like those of many universities, has options of getting alternative sources of support, and the QR links to that. So that's a first set of information about PhDs. There is something new that starts this autumn, which is the York Mathematics Department is now a partner in the Martingale network. Martingale is a charitable trust. They have a lot of money behind them, and they have a focus on supporting students from low socioeconomic backgrounds who are eligible for UK fees. So this is much more aimed at UK students who may be watching online or in the recording. And the result of this is that we're going to have up to 3 Martingale PhD scholars per year, plus also master's places as well for our taught MSc. And those are also focused on mathematical physics and pure mathematics. It's a very interesting choice that Martingale have made, and they made it deliberately, I think, because they think that there is money for other things and other people should put their hands in their pockets and pay for it. So they have decided that they are focusing on mathematical physics and pure maths. The way you apply is somewhat different. You apply directly to Martingale in the autumn. So applications already on the 12th of August, you apply to become a Martingale scholar, and then, armed with your scholarship, you approach universities, who of course will be delighted to find a fully funded student who's also probably very high quality, turning up on their doorstep and asking about supervision. So that's Martingale, that's completely new. Not all universities in the UK are Martingale partners, so it's about 8, I think, in total at the moment. So it's really, we're in quite a good company there. Now turning to postdocs and beyond, how do people join us as postdocs? Well, one way is, of course, through direct appointment. If somebody gets a grant with a postdoc on it, then we advertise. And the standard place would be to look for that, such adverts as Jobs AC UK. Daan and Stefano have come under that route. Daan on the grant that Kasia and I have, Stefano on the grant that Benito has, which is also his fellowship. But the main route, I would say, or probably the best traveled route, is to get an independent fellowship of your own, which means it's your money and your research program, and it gives a lot of freedom to pursue it. I have written down a list of potential sources of early career fellowships, roughly speaking, in order of when you could possibly apply for them in the course of your career. So LMS is very much right out of PhD for a short period of time while you're getting some publications out and looking for the next longer thing. And you can see this runs up to things like the Royal Society university fellowships, which are major, up to 7 years or so in funding, and run slightly below that, but still a very major fellowship of the EPSRC fellowships, the early independence ones, which replaces the open fellowship that Benito holds. So these two are the most prestigious on the list, and biggest in terms of the amount of time and funding that you can get. But actually, a number of these are actually quite difficult to get. They're quite prestigious if you do get them. And we will hear from a mystery speaker in a little while about their experience. So I'm not giving anything away as yet as to who the mystery speaker is, but we will have a little bit more about how that happened. As you see, we have populated a reasonable amount of this recently within our mathematical physics group. And I would say also that elsewhere in the department, for example, we have a current Leverhulme fellow who's working in number theory. And we have a current, Eleni was a former, fairly recent, but former Marie Curie fellow. And we have a current one who works on stochastic analysis. So as a department, we've actually populated quite a lot of this in recent time. So we do have experience of supporting people to get them. That brings me to the second part. Sounds a little bit daunting to get your own fellowship with your own research project. Well, we can help. We have two main sources of general help. They are Alexandra Lano, who is our Research Environment Development Coordinator. She had a previous career as a postdoc in biology and got her own funding under those circumstances. So she's actually very experienced as a researcher in her own right and about understanding the postdoc situation. So we're very fortunate to have her. And then as an academic colleague, Professor Victoria Gould is our fellowship lead. We say champion in the department, but that is not quite clear what that means if I just say it. Among the things we do is run a scheme called the York Mathematics Fellowship Development Bursary. These allow for about £1,000 for a potential fellowship writer applicant, I should say, to come here and work on their proposal with a specific academic and also getting advice at the same time from Alexandra and maybe Vicky as well. So these get advertised regularly, 1 or 2 rounds a year, usually in the late spring. And that would be advertised, for example, through the department website. A QR code will tell you how to get that. You should make contact with an academic sponsor in the department first. I think now it's time for the mystery speaker. Is that correct? So I am going to call forward. Who is it? Who could it be? It's actually Patricia who's going to tell us a little bit about her experience applying for, and even better, getting an independent fellowship at York. So I'm going to move out of the way for a little bit. I'm going to move this way, actually. Patricia.
Well, so first of all, let me thank Chris for inviting me to participate and share my experience about, the thing that probably many people who are finishing their PhD are fearing the most, how to find a postdoc. And in particular, what you can do once you find one. If you are a little bit, let's say, well, I will tell you about that. Anyway, first let me introduce myself a little bit and tell you what my career path has been so far. So essentially, I did my bachelor in physics at the University of Barcelona. You can see the first star over there. Then I moved to Germany, in particular to Munich, to do my master in theoretical and mathematical physics at these 2 universities, Ludwig Maximilian University and Technical University of Munich. Then, since 2 countries was not enough, I decided to move for a PhD to the Netherlands, where I did my PhD under the supervision of Beatrice Bonga and the unofficial supervision of Ivan Agulló at Radboud University. And then the moment came when I was going to decide what I was going to do. And perhaps since I'm here, you can already say that the end of the story, at least for the moment, is that I ended up at the University of York. Very well, so how did I get here? So let me take you back to when I was, doing more or less in the final year of my PhD. So I had a wonderful experience. And actually, I decided, hell yeah, this is for me. I want to continue in academia. I really like what I'm doing. But now comes the difficult part. So how do I look for a postdoc? And perhaps for some of you here in the audience, and perhaps also for the people watching online, who are now in the period of application, well, you will agree with me that finding a postdoc is kind of a maze based on, well, full of things that you don't really know how to do, and where you are going to mostly experience a little bit of rejection, well, a lot of rejection here and there. So it can be kind of a frustrating process. The way I approach it, as advised by my supervisors, was first to start looking early. And one thing you can do is try to think what is what you want to do after this. No? So then I went trying to ask myself the question, okay, so where do I want to go? What do I want to learn? And the first thing I did was essentially to try to draw a list of dream places. So where do I think I'm going to fit the best, where I can, learn the most, where I can do what I want to do. But then also everything else. So I'm not going to bore you with the details. I will just tell you that, not surprisingly, actually at the top of my very list of dream places was the University of York, because I had been following for a while, even if I hadn't met directly, the research that Kasia, Benito, Chris were doing. And I thought, this is the place where I want to be. So then I started looking for opportunities to apply to York. But okay, also displaying very little, let's say, dignity, I just applied everywhere else. Now, once this was done, turns out that at some point, there was a position that opened, Benito's position. And I was super excited. I thought, this is my opportunity. Maybe, they get to meet me. Maybe I can make a case. And maybe, I can get it. So I prepared for the interview. I read my papers. And I thought I was prepared and ready. And I went to the interview. And I thought I went terribly wrong. I can tell you. I was writing my PhD thesis at the time. I hadn't had food for a very long time. Was super stressed. I almost passed out in the middle of the interview. So I'm telling you, it went wrong. Benito doesn't think so. I don't know how. But it didn't go well. So, that was a bit of a setback. So then I started thinking, so what do? I have two options, really. One is give up, pretend these people never ever saw me, because probably they think I'm an idiot, or, find alternatives. And, since by then I was really convinced that, this is going to work out, giving up was not an option. So then I started doing my homework, and I started trying to find fellowships that could allow me to come to York nevertheless. So then, you cannot imagine right after that interview, the crazy amount of work and obsession that went into, researching possible fellowships. And also thinking of potential projects for those fellowships. So I was about to write an email to Benito saying, hey, I know you probably don't want to hear from me, but I was thinking, I could apply to this with you if you don't hate me. When actually I received a call. A call that I was certainly not expecting, telling me that somehow I had managed to get the position. So, I was super excited, I was super happy, but on the other hand, I had already invested a lot of work into looking for fellowships. And we all know that it can be advantageous to have your own money at this stage and this age when, getting from one position to the next can be very challenging. So I thought, maybe I can run this idea by Benito. So I got all the courage he got, went to Benito and asked politely by email, hey, I know there are these options, so what do you think? Maybe I can apply as well, and we see what happens. Now I'm in a good position. I don't have to worry about it. Okay? And Benito was absolutely amazing. Everything that happened from there is not something I did alone. Everything that happened from there was thanks to the support of the people here, the support of my supervisors. So they encouraged me to actually apply to some of these things, in particular, the 1851 Research Fellowship. And, the first draft and the last draft, or the version that was submitted, do not really look much alike. So I can tell you that was thanks to the feedback that I got. And, so long story short, a lot of work was invested into that, but finally, I did get 1851 Research Fellowship, which essentially allowed me to come here and both collaborate with the wonderful people here, as that was part of the research project, but also be able to develop a little bit of my own program. So as a piece of advice, or what I learned with all this story, is essentially, start early when looking for postdocs, and perhaps, don't wait for opportunities. It's difficult enough. If you find something else, even if you have a good opportunity, maybe don't settle so easily. Just go for the next thing. And finally, ask for help. I wouldn't have been able to do this alone. So that's, in any case, the strongest message I want you to think. You want to come here, contact the people here. They are amazing. They will help you. So, thank you.
Thank you, Patricia. So just a couple more things from me before I run out of time. Two sets of tips. So when I was preparing this, I did look at some of the other career development talks in the circuit. And in particular, I looked at the Manchester one, which was just a couple of weeks ago, I think. And there was a segment there by Ben Carter, who actually knows what he's talking about, because he has career development, I think the title is, as part of his job. And so I would recommend looking to see what he says. It was clearly an even hotter day there than it is here. So that's the first tip. The second tip is about fellowships. So there are many aspects to writing a good one, but there is a very simple core which comes in 3 words: person, project, and place. And so really it is why you? Why should you be doing? Why should you be funded? These are quite large amounts of money that are being thrown around. So why should it land in your lap? Why this project? Same questions. A lot of money. Why this project is worth all of that? And finally, why you with this project in this place? Because if you apply to come here doing something that none of us do, well, that's probably a wasted opportunity for you and not really great for us either. And the funding bodies will smoke that out and you frankly will not get the money. Okay, so there has to be a good reason for why you with this project in this place. And the things that you might think of under that category are: what is the added value of doing this project here in York, for example, and are there bi-directional benefits? Do you bring something that we don't have, and can you get something that you don't have from us? So that's a very, very small set of tips, and I think at that point I just go immediately to questions. Thank you.
Has some questions, I think Chris and also Patricia, I guess, will be very happy to answer them.
Just a standard question, I guess, after this type of talk. So, are there any open positions right now? Is there any perspective of when a postdoc or PhD position in the group with you, maybe with Kasia, maybe with Benito, will open soon? And just, how competitive would that be, or anything like that would be very useful?
Right. So in terms of open positions right now, I don't believe that there are any. In terms of what's coming up soon, not quite with us, but elsewhere in mathematical physics, I think that there will be a postdoc advertised. This would be more in the direction of integrable systems and quantum field theory. That is, I think, coming later this year or maybe early next year. So there is a postdoc position there. All the fellowships, of course, remain open. The funding that supports Daan is coming to an end. So it probably is not a surprise that we will be looking to find some additional sources of funding. So if we're successful, then who knows? But that is the possibility. In terms of competition, they are very competitive positions. So that's the same story as everywhere. Benito had, what, 60-ish? How many fingers is that? 70 candidates for his postdoc position, for example. That's possibly the slightly higher end, but it gives you an idea of the numbers. It should be said, of course, that out of that recruitment exercise, we ended up with 2 postdocs, because Patricia then neatly got her own fellowship.
Thank you. I was wondering what opportunities there are to perhaps boost interdepartmental fellowships or postdoc, kind of just positions where, say, you've got a foot in physics and a foot in maths, or because from what I can tell, they seem to be quite separate in terms of the communication front between the departments, even if there's large areas of overlap with the research? And do you have any comments on how we could go about improving the inter-department sort of connectivity?
Yes. So one answer to that is talk. There are some on this list where you really have to be squarely in mathematics. And for example, the EPSRC Postdoctoral Fellowship and the EPSRC Early Independence Fellowship, those are initiatives of the mathematics panel within EPSRC. So the community as a whole, or the part of it that gets a voice, has decided, I think correctly, that for mathematics it's worth putting a chunk of the total money for mathematics into fellowships. That's not the decision of other panels. But for that reason, if you want to apply for one of these things, it's got to look like mathematics, right? So the people, I mean, that's why, unsurprisingly, the fellowships that we have through these routes are at the mathematical end of quantum field theory, because it has to convince a panel of mathematicians, which of course includes mathematical physicists, but it also, there will be number theorists, there will be algebraists. They have to say, yes, we're happy that the money goes to someone in mathematical physics over probably, maybe a number theorist and an algebraist. So that's the argument that has to be swung, if you like. But others are for the candidates. So for example, I mean, just going to the top of the list, Royal Society aren't going to care if you're in maths alone, in physics alone, or somewhere between mathematics and physics, spending half of your time in each or with mentors on either side. It's always possible to throw in a mentor. So even with these ones, if you've got a proposal that looks like maths, you can have a mentor in physics. And indeed, Maté, for example, applied for something recently with a co-applicant from physics. So these things are certainly possible. They require dialogue and a plan for how it works. But yeah, the first thing is to make those contacts. I think there's a follow-up.
Yeah, I was just wondering, in terms of what would you say is the difference between mentor and supervisor?
That's a very good one. So I said this list is organized by, broadly speaking, experience. Okay. So LMS Early Career Fellow, this is, as I say, right out of PhD. So you don't necessarily expect someone to be completely research independent. So they are going to need someone who is fairly well guiding them. They're also quite short, so you can't spend a couple of months working out what you're up to. You need to get going on them. So these ones the earlier ones tend to have supervisors, but the independent ones, so this one is much more tied to having a supervisor, mentor. These ones here, the money is, for example, Patricia's, or the money is, for example, Christiana's. Okay, so on the other hand, they will have a mentor, a figure in the department. So in Christiana's case, it's me. In Patricia's case, it's Benito, who is a sounding board and someone that probably will actually work together on some part of the project. Okay, but for example, Christiana and I work together about half of Christiana's time, and I can't tell her you've got to make that 75% because it's her fellowship, right? So that's the sort. So I'm not a supervisor. I'm more of a mentor in that and collaborator in that way. Marie Curie, I think it is described as supervisor. Again, this is relatively early, 2 years, and they are interested in the development towards independence. So that's why it's a supervisor rather than a mentor. So each one is different. Royal Society, by the time you get to that, anyone who can get one of those doesn't need a supervisor, but they will still need a mentor for advice about how to pitch things, how to organize conferences, workshops, all of the things that you might need advice about, and just general yearly or regular monitoring. How's it going? How do you feel the research is going? Do you need some advice to, if someone's getting bogged down or something like that, how can you get them out of that hole? Get them to get themselves out of that hole. Does that help? Yeah. Yeah.
I just wanted to add to your question, perhaps, that there are some fellowships specific to develop between theory and experiment. And I think those would be a good fit. One example is the Enrico Fermi fellowships that are now open, and I think fund about 1 to 2 years of research, end of PhD and first postdoc. So that would be an option for closer collaboration between some, mathematics department and someone in physics a bit closer to experiment, if that helps.
Okay, so thanks again very much, Chris and Patricia. And we should clap.
Thank you.
I think it's good time to move on with the first speaker of this session.
There's a furry thing.
Ooh, you know I like those. Sorry? Control L. Control L, yeah. Wow. Yeah. Magic.
Okay, so I think we should start. We're a bit late, but we will take some time from the coffee break maybe. I'm very pleased to introduce Kasia Rejzner. She's also a professor here in York, and she will tell us about quantum reference frames and semi-local observables in QFT.
Okay, thank you very much for inviting me to York. I enjoy being here a lot, also because I live here, but that's my first time on the RQI circuit, so it's a great pleasure. All right, so for those of you who don't know me, I work on algebraic quantum field theory. I'm part of this York group that Chris was talking about. And this is essentially a framework to study conceptual problems in quantum field theory. And the idea goes back to Haag and Kastler. In the 60s, they had this idea for describing mathematical foundations of QFT on Minkowski spacetime by specifying algebras assigned to regions of spacetime, sorry. So to each region we assign an algebra, and if we have a larger region, then we expect to find more observables in that region. So the theory is specified by a net of algebras that are interpreted as algebras of observables. Okay, and for things to have some more physical meaning, we also require some further properties called axioms. So first is the causality. So if we have two regions that are space-like separated, then we want the observables to commute. And the second property is about evolution. It's called the time slice axiom. So it says that if we know these observables in a thin time slice, then we know them everywhere because there is some sort of dynamical law that governs the evolution in time. Okay, now, meanwhile, we can do it also on curved spacetime. So this is the main topic of my research, actually. It's QFT on curved spacetimes. So we replace Minkowski by another background, so a cosmological background or a Schwarzschild or some other completely generic background as well. Although we do have a class of spacetimes that we like the most, which are called globally hyperbolic. But the philosophy is essentially the same. So we still assign algebras to regions, and then we require the causality and time slice axiom. And moreover, we can also do it covariantly across the whole class of spacetime. So Benito was also talking about related things. And we can also do it perturbatively. So if you're not happy with C-star algebras and von Neumann algebras, or you don't know where to find them, then you can construct your algebras using formal power series perturbation methods, as one usually does in quantum field theory. Okay, and if you want to read about that there's a book that, if you're interested, you can ask me for. Okay, so now we know all that, and that was the state of the art for a long time. And people kept asking, well, you know, you talk about observables. So how do you observe them? How do you actually measure them? Why are you calling those observables? And for a long time, people in my community were just giving this slightly embarrassed look and would shuffle out of the room and pretend that nothing happened. And then Chris, who now left the room, but I'm sure he will be back, and Rainer Felch from Leipzig, they actually decided to finally do something about this embarrassment, and they came, oh, here you are, came up with a measurement scheme that works in algebraic quantum field theory. So Chris is here, so he can definitely tell you more. I'm just going to present a cartoon of how this works. So the first important feature is that we are actually talking about measuring one quantum field theory using another quantum field theory. This stays within this AQFT framework. So these are two nets of algebras, and they're coupled. So they talk to each other, and they talk to each other only in the compact region that I denote here, K. And so we can, well, consider the coupled theory, C, but we can also consider a theory where they don't talk to each other, so this is the uncoupled theory. And, well, because the coupling only happens in this little compact region, in the future and in the past of that region, there is no difference between the coupled and uncoupled theory. And yeah, so one of the two axioms I gave at the beginning is going to become very useful because, as I said, if you know operators in the thin time slice, you know them everywhere. So in fact, because coupled and uncoupled theories look the same around a time slice here in the future and around time slice here in the past, then we can use these identifications to actually construct maps between coupled and uncoupled theories. So one is induced by the choice of some Cauchy surface in the past, so that's tau minus, and one by Cauchy surface in the future, that's tau plus. Okay, so I have those at my disposal. And then I use them to transport things like observables and states between coupled and uncoupled theories. So I start with preparing a state for the probe in the pre-coupling region, which is blue. Okay, and then I measure late in the post-coupling region, which is here. Okay, and then I compute. So expectation value of this probe observable will tell me something about the induced system observable localized in some region containing this coupling. So I can read out information about the system by doing measurements on the probe. And yeah, you can also ask the opposite question, and it has been answered in several papers. What is the correct choice of the probe observable to have a particular observable as the induced system observable in the outcome? So this has all been studied and is still under development. There's always a space for building more models and understanding new phenomena. But in a way, well, this is the established framework. This is take it or not, but this is a measurement scheme for QFT. Now, okay, why am I talking about it? First of all, because I like talking about it, but also I want to point out that there is something important about this choice of coupling region, that these things couple locally and in a compact region. Because, well, what if I'm in a spacetime with symmetry? And many nice spacetimes have symmetries. Well, Minkowski has plenty, but also other nice things. De Sitter, Schwarzschild, Friedman, Robertson, Walker, they all have symmetries. So, well, Obviously, my theories, my quantum field theories, they transform under these symmetries. So typically, we require them to be covariant with respect to the background symmetry. But this coupling region will move around. So this is not invariant, okay? So let's say that we are in Minkowski and we are thinking about a measurement that takes place somewhere, sometime, but then we can apply time translation. This is one of the symmetries of Minkowski, and then we have the same experiment at a different time, okay? So here is the picture. So what do we do? Okay, so that introduces a certain redundancy, certain extra freedom, because in order to be able to specify what measurement are we talking about, we need to specify, for example, the hour. So we need a clock to tell us where we are here. And more generally, we need something to label elements of our symmetry group and tell us, which of these measurements from this whole orbit under the action of the group one should be looking at. Okay, so normally, I mean, this is what happens in classical physics too, okay? This is what happens all the time because things are symmetric, and it does happen that we measure something today and we measure something tomorrow, and obviously we know it's either today or tomorrow because we have a calendar, and I even have a clock, and I even changed the hour after I came to the UK from continental Europe, so I even know the time here. But so we don't think about it, right? We know what to do. We just need a reference frame. So we need, in other words, another physical system that tells us, for example, what time it is. Now the problem is if we want to have everything described in a fully quantum way, the world is quantum. I think that hopefully I don't need to convince you about that. So in order to specify another physical system for our labeling space, this has to be also fundamentally a quantum system. This is where quantum reference frames come in. So a QRF is going to be another quantum system that will provide a set of labels for our measurement, and that set of labels will come from some observable that is also covariant under the symmetry group. Okay, so what are the physical observables? Now that we are aware of the fact that we are always implicitly using some sort of reference frame to label time or space or whatever other symmetry we have, now that we are aware of that, then our true observables, the things that we actually measure, just to come back to this question, are observables in the net really the things we measure? Well, to a point. However, if we take this idea seriously, that all the information that we can actually obtain is relational, so it's from the relation between the reference frame and the operators, local operators in my net of algebras, then the invariant observables, those that are invariant under the symmetry group, are in fact joint observables of the system and the reference frame, invariant under the action of G. So the real object of our study is actually that space. And okay, I could finish here and say, well, that's what it is, and people should just do it, and why do you bother me? But yeah, well, first of all, there are many approaches to quantum reference frames because, one could ask a very good question. So what is a quantum reference frame? So what are you talking about? And there are some answers on the market. So main approaches that I'm more familiar with are the perspectival, perspective neutral, and operational, but there are many more ideas on the market. By the way, I'm going to do advertising as well. there is going to be a conference about quantum reference frames in Waterloo, October 26th to the 30th, at the Perimeter Institute, and you still have 2 days to submit abstracts if you're interested in coming and giving a talk and enjoying quantum reference frames in a friendly environment. So please do come, and commercial break. Okay, yeah, so there are several approaches, okay? Now, in quantum field theory, well, this is relatively new, let's say, okay? And in algebraic quantum field theory, this is even newer. So it's still a lot of work to be done, but we already have some examples of applying operational quantum reference frames in this context. So there is the simplest example is when the quantum reference frame is a quantum mechanical system, not a QFT, and it serves as a reference frame for a QFT. And this was done in the paper from 2024 with Chris, Dan, Leon Lavridge, and James Waldron, and it was inspired by a model proposed by Chandrasekhar, Longo, Pennington, and Witten the year earlier. And this was about, well, quantum field theory coupled to essentially a quantum mechanical clock acting as a quantum reference frame on the Sitter spacetime. Okay, a more interesting example, I would say, because of the added complexity of having one quantum field used as a QRF for another quantum field. There is a paper with Chris and Dan, slightly more recent, where this quantum reference frame is actually given by edge modes in electromagnetism, so it's given by honest quantum fields on a spacetime with boundary. So I will spend more time talking about it in a minute. Then one can also do that asymptotically. So instead of finite boundary, we can take compactified boundary at infinity. So this is work in progress. And finally, I want to connect to another older paper of mine with Brunetti and Fredenhagen, where we constructed relational observables for perturbative quantum gravity using dynamical local coordinates that can also in some way be seen as a quantum reference frame. Okay, so these are the examples we have at the moment. So let me discuss the one with electromagnetism on the spacetime with boundary, because I think this is really non-trivial, and there's new quality here because of using quantum field theory. So we consider spacetimes which look like this. So they're called Cauchy lenses, and they are made from two Cauchy surfaces glued together at the edge. So there's a boundary made of these Cauchy surfaces, and there's a corner where they are glued. And the action is the standard electromagnetism with external source. The equations of motion are not surprising to anyone, I guess. And we can consider the space of solutions. Okay, easy peasy. Now, a slight complication is that now we are looking at the spacetime with boundary. So there will be some subtleties about that in terms of solutions and symmetries. So we know we have gauge symmetries, right? Electromagnetism, gauge theory, U1. That's also not surprising. But here there are essentially two important types of gauge theories, gauge symmetries to distinguish. So there are the gauge symmetries that vanish at the corner, that live in the bulk. So they are these redundancies of the theory, typical local gauge symmetries that we had in the situation without boundary 2. So first, let's get rid of those. So let's quotient our solution space by those symmetries. And there are the remaining ones that have non-zero value at the corner. And, well, we call them corner symmetries. We can call them many things because people call them many things. But I think the important part is to distinguish them from the bulk one. Yeah, so this is, well, mathematically what they are. So those symmetries induce neutral charges that then correspond to fluxes through the corner. So they measure the incoming or outgoing flux through the corner of our Cauchy lens. Okay, so these are fun things. And that group, that second group of corner symmetries, this is now going to be the group, the symmetry group for which we are constructing the QRF. And well, this group is infinite dimensional. It's not horrible, but it is infinite dimensional, so that's another, maybe let's say, technical complication of this story. Okay, so let me show you the classical observables. Next, I'm going to show some pictures instead of actually defining things because I have limited time. So let's look at everything on the Cauchy surface. So this is projected at any Cauchy surface within the Cauchy lens. So we have things that are, well, sort of smeared Wilson loops and Wilson lines. So there are either closed ones or open ones attached to the corner. And there is the smeared electric field. And these two types of observables, they form a canonical pair. So they satisfy equal time commutation relations. So first, so there is their Poisson bracket, symplectic structure, and then this will be quantized in a fairly standard manner, actually. So we can, yeah, so, okay, so we solved the problem first on the classical level. Then we used the Weil prescription to construct the C-star algebra, because we like C-star algebras, of the symplectic space of observables. Yeah, so what's new? Okay, including or without questions, sorry?
Without questions.
Okay, okay. So I will speed up. But we started late.
By without question, I mean after these questions.
Ah, okay, good, good. I thought I miscalculated. Thank you. Okay, yeah, so these observables in the symplectic space include observables that have non-vanishing value at the corner. So this is somewhat different from a situation without boundary. Okay, and then in this paper, we have demonstrated that you can construct also Hadamard states for such algebra, and if you find yourself in a particularly nice representation, so you can construct the Fock representation, you can complete your algebra into a von Neumann algebra. So that's the best situation you can be in terms of function analytic properties. So we are done with the algebra. And now let's go back to this QRF story. So what is the QRF? So the QRF is now going to be provided by variables that are supported at the corner. So these are, well, essentially, yeah, something like edge modes. And what do they do? So if we take a bare observable, so for example, I think I have a better picture later. Okay, so yeah, so we have a Wilson line that's just floating around, and it's gauge covariant. It transforms non-trivially under these gauge transformations that have non-vanishing values at the corner. So then we can use those edge modes, those variables at the corner to sort of attach it, so to specify addressed relational observable, which is a sort of yeah, now it's an element of this joint algebra of this sort of bare observables and the QRF localized at the corner. Okay, and moreover, there is an actual very practical prescription for doing it. So we were using the framework of operational quantum reference frames, and there is the Yen map, which explicitly constructs from a bare observable, a dressed observable that has now this corner data. Okay, so that was fun. We had to face the problem of the group being non-locally compact, but this happens. So we had to do some limiting procedure, but that worked. So the take-home message is that, relativization here takes an open loop and attaches that to the corner data. It gives you the dressed observable. But there's also another way of thinking about it in terms of gluing. So let's say you had your algebra of observables, including Wilson loop, in the torus, and then for some reason you decided to cut your torus because, well, let's say you had a donut and you wanted to share it with your friend, and then they are complaining that they have those Wilson loops inside that are not gauge invariant. That's, you see, friends for you. You give them donut and they always find a problem with it. So yeah, so you can tell them, look, don't worry, all the data is still there. Look at this. I take these two pieces, and then magically, using the Yen map again, I can glue them and reconstruct all the observables, and everything's fine. But yeah, don't try this at home because it's a tricky business. Okay, so that was this example. 1 minute. Okay, 1 minute. So let me just say very quickly about the last step, and this is the work in progress, so I cannot say much about it anyway. So, but yeah, so there was this idea in the paper with Brunetti and Frenhagen. Actually, it's from 2013, but took 2 years to publish. That to construct diffeomorphism invariant observables in perturbative quantum gravity, one can use the idea of relational observables, and the concrete construction we proposed was to choose 4 scalars constructed from the metric and the matter fields that we call dynamical coordinates, dynamical local coordinates, because they actually depend locally on that data, and they act as the choice of coordinates, of reference frame, observer, whatever words you want to use there. And then we choose a background value of these scalars such that this map from spacetime to R4 is injective, so they are actually honest to goodness reference frame. And then we perturb a bit and then consider a map which goes from spacetime to R4 and back. So spacetime to R4 using the background coordinate system and back using the perturbed one. And then this transforms nicely under diffeomorphisms. And if you combine it with another scalar, then you get something invariant. Okay, so this smells very much like a quantum reference frame. So we hope to understand that more precisely. So to phrase this in the language of operational or any other quantum reference frames, if you have ideas. Yeah, I think the rest is just bonus content. So thank you very much for having me. And yeah, thank you very much for your attention.
Thank you, Kasia. I think we have some time for 1-2 questions from the audience. Otherwise, I ask, okay.
Thank you for the great talk. You mentioned that there are several approaches to QRFs. Mm-hmm. Could you explain to someone from out of the field what are the different, like the differences and the similarities?
Well, I mean, there are papers written about it, and I think right now there is, so the ones I'm actually at all familiar with are perspectival, perspective neutral, and the one I'm working in is the operational. Yeah, so I mean, they differ a bit about the philosophy of what you're describing, and yeah, what is the meaning of a quantum reference frame? Yeah, I guess my choice is the operational because it has a nicest mathematical definition. But yeah, I mean, it's hard to really summarize it in 5 minutes. So I will send you to some very nice review papers recently comparing between these approaches. So I think I don't want to say too little. Yes.
Perhaps a few sort of sprinkle of what is the difference. So for instance, in this perspective, so operational, which is what we're familiar in, is really about what are the invariant observables that, let's say, in all reference frames, so to speak, would agree on. So it's really observable focus. The other approaches are much more about, let's say, Hilbert space based. So the perspectival is about what does, let's say, this state, say you have two particles and there are two particles, what does the state of the system look like from the perspective of one of the two particles, so to speak. And they try to make this somewhat precise, at least, well, they try to do things with this. Then there's the perspective neutral approach, which is much more about, can we describe a state which essentially is sort of gets, you can think of it roughly as, okay, it gets into the center of mass perspective, so to speak, but it tries to get rid also in your Hilbert space, so to speak, of all sort of redundancy. But since Hilbert space representations for us are not the most meaningful things, they're a bit of a, well, they're not really the object we study in for us, the operational
We
approaches.
like algebras.
Yeah. But if you really care about, okay, I have this two-particle representation, I cannot actually measure the sort of individual positions of the particles, what is the sort of minimal Hilbert space representation that I can find to get both of these? So this is this perspective neutral approach, roughly speaking.
Okay, so let's thank Kasia very much again.
Thank you.
Yes, well.
It's on mute.
Maybe it's been all on mute then. I hope not. Is it currently, how do you actually? So, okay.
No, let me introduce the next speaker. The second one, I think it's in continuity with the last question also of previous talk, because it's Daan from the University of York, who will tell us about measuring relational observables. So, please.
Yes, hi. Okay, I hope I'm unmuted now. So indeed, it's actually very nice that Kasia gave this talk before me, because a lot of the motivation was also in Kasia's talk, so I can be somewhat brief about this. So yeah, I want to talk about how would you measure relational observables. Of course, I will have to first explain what I mean by relational observables in a bit more detail, but it's going to be very much related to what Kasia talked about, quantum reference frame, this idea of relativizing things. But what is the motivation behind relational observable quantum reference frame? You want to describe quantum systems in terms of, let's say, invariant quantities under appropriate symmetries. And the rough idea that where this comes from, or one way of getting to this, is that you imagine, well, actually the ultimate description of our universe, so to say, should be some theory of quantum gravity, which is in the moment in some kind of head in the clouds. We don't really know what it is. But if we take sort of general relativity as a guide, it should be that the physical observables are somehow diffeomorphism invariant. They shouldn't depend on choices of coordinates on your spacetime whatsoever. Now, we do quantum field theory in curved spacetimes, which under some, let's say, loose notion of limits, one can view as a sort of fixed background limit of, okay, instead of having a dynamical spacetime, or let's say we have sort of superpositions of spacetimes, whatever that means, there's somehow a fixed background spacetime that we're working on. And you would expect that under that limit, say you have some observable here that depends on the metric, the quantum fields, etc. around. You take this limit, you fix the background metric in this observable. What you end up with are observables that should be invariant under, well, whatever symmetries of the background you are working on. Now, of course, in our day-to-day description of quantum fields, we use, let's say, fields smeared with a test function at a certain point, but this is not an invariant quantity. I can translate this test function around and the observable will change. So how do we reconcile this? Well, it's the idea that the system observables that you describe should somehow be obtained from relations between systems and some other, well, reference frame, some other quantum system, or well, some other system which might as well be a quantum system. Some people have thought of this, oh, this is the observer. So it's about the relations between the quantum field and the observer, or, well, some arbitrary other quantum system. And this has led, well, this is this paper by Chandrasekhar, Longo, Pennington, and Witten to look at these algebras on invariance between quantum field and some external system, and they found that this has some interesting algebraic properties, and we've generalized this quite a bit in this paper that was mentioned here. I will, at a later point, explain a bit more what I mean by regain sort of system observables from this. Now, what I actually want to talk about in here is how would one model the measurement process of such a relational observables. So we've seen in earlier talks how to model measurements of the observables of a quantum field. How would one, let's say, model measurements in relation to some quantum field? So let me just, here's the sort of sketch of a measurement scheme from sort of various perspectives. You have a measurement scheme which involves some interaction in some bounded region, but this breaks the symmetry of your spacetime, of your background usually in some way. So this is a point we make here, but one can make this quite precise, is that if you have your couple theory is covariant in some sense under the spacetime isometries and this, let's say, time translation on Minkowski spacetime, then the only measurements you can perform are sort of trivial ones. So if you want to make non-trivial measurements, you have to break this time translation symmetry in your quantum field. And the idea of these measurements is, as was discussed before, you have a system and probe, you prepare the probe in some system, you interact them in some way, and then you read out a probe measurement, and from that you infer things about the system. So what this means is that, okay, through such symmetry-breaking measurement schemes, one will measure observables that are typically not invariant under your symmetry. So what we want to do is define these measurement schemes somehow in relation to a reference frame, and by that end, measure relational observables. That's one way of thinking about this. So how will I discuss this? I will actually do very little quantum field theory in this talk. I will do some sort of generic abstract description from the perspective of let's say, well, algebraic quantum theory in some sense. But so I will need a bit of math. I will talk about von Neumann algebras, which is the mathematical settings, group actions on them, and I will specify a bit more what I mean by an observable in this case. Then I will discuss what I mean by a relational observables, and Kasia mentioned this idea of, okay, these should be invariant under some invariant observables in some together with some reference frame, but one can also have a slightly covariant perspective on it, which I will discuss. I will briefly say something about these measurement schemes in this very abstract von Neumann algebra setting, and I will then, from that, tell what I mean by relational measurement schemes, and at the very end, if I have some time, I will talk about how to maybe implement this in quantum field theory. Okay, so what is a von Neumann algebra? Well, we've talked about star algebras before. Now I want star subalgebras, algebras on some Hilbert space specifically, because I want to talk about, let's say, well, von Neumann algebra is in particular a star subalgebra that can be represented on some Hilbert space and is closed under what is called the weak operator topology. Now, this is a bit of a technical mumbo jumbo. What one has to remember is you can take limits in this algebra in some sense and still end up with elements in this algebra. And in particular, what I want to use this for is that I want to be able to integrate certain things. Now, what is an observable? This is a slightly this is a more generalized notion than what was discussed previously as just some self-adjoint operator. What I want is some positive operator valued measure. And what is this? This you can think of as some, there's some sample space of possible outcomes of a measurement of that observable. F as measurable sets, but you can think of this as sort of subsets of the sample space. And to that those subsets, I will assign some operator in between that is sort of larger than 0 but smaller than the unit in that algebra. In particular, such that if I enter the whole sample space, I end up with the unit. And the point is that if you have a state on your algebra, a normal state, which is a state that is, let's say, continuous under this topology, technical details, you end up with a probability distribution on this sample space. So here you take the trace with respect, this is just a sort of abstract representation of what it means to take the trace with this density matrix and this measure. And the prototypical example is a projection valued measure, a spectral measure, which is you take a self-adjoint operator on your Hilbert space, you sort of decompose it into its eigenvalues. Well, this might not be a discrete spectrum, but this still makes sense, at least in this von Neumann algebra language. And this measure here is such a positive operator valued measure, taking values in a projection. So how can we think of this generalized notion of observables, which is now not longer necessarily projection valued? It's a self-adjoint operator plus some potential noise. Okay, what do I mean by symmetries in this mathematical setting? Well, I will restrict myself to something called W star dynamical systems, but because I'm also talking about systems in some other contexts, I will refer to them as W star G algebras. This is not standard terminology, but saved some space on later slides. So it's a von Neumann algebra, but also some group acting on it through, let's say, a group action alpha, which you also need some continuity requirements such that things make sense. And this group G, which will be some, well, for now, locally compact, second countable, topologically nice group. Think of isometries of a spacetime. One can take invariants in that algebra, which I will just denote like this. So these are the operators in A that remain unchanged when you act with this group action. And what we're going to consider is a system, so that's why I'm just going to call these a W star G algebra, which is, let's say, you can think of the quantum field that we want to study, and there's some reference, which is some other quantum field, some other quantum system, whatever, having also a group action with respect to the same group. And the nice thing is about von Neumann algebras, we can take tensor products in a nice way, we can also tensor these group actions together, and we can look at joint invariants of this algebra. Now, in a very what do I then mean by relational observables for this system algebra A? Well, at a very sort of abstract level, it is just an observable living in this invariant algebra with respect to this reference. So this is what I mean by R relational for A. I take the invariants with R, A tensor R, and look for the observables in those. Now, if you take now a partial trace with respect to a normal state in the reference, you end up with a system observable again. And this assignment from states on the reference to observables in the system satisfies certain properties. There's some kind of mixing relation. If I take a mixture of two states on the reference, I end up with a convex linear combination of these observables. It's covariant in the following sense. I can, if I change the state, if I sort of move the state of the reference around, then tracing it out will just give me sort of changed system observable. And well, there's some continuity because of this being a von Neumann algebras and this being a normal state. Basically, if I evaluate this observable A row in a state of the system, this is like taking observable A here and evaluating it in a tensor product of these two states. And that gives you certain continuity requirements. particular, this is continuous with respect to the operator projective tensor product topology on the normal states. Anyway, there's a very neat result which works nicely for von Neumann algebras, which is partly why I'm working in this setting, is that there is now a one-to-one correspondence between these R relational observables and any, let's say, map from sets of this reference frame, from states of this reference to these observables in the system satisfying these three qualities. So that's nice. These are sort of two different ways of thinking of a relational observable. An example, an important example, which touches on what Kasia mentioned, is that you have this notion of a quantum reference frame or an operational quantum reference frame. And for simplicity, I'll stick to a principal quantum reference frame. This is just unobservable in the sense that I discussed before in this reference algebra that is covariant in some way. So let's say it acts like the possible outcomes of this observable are elements of my group. And if I act by the group action on this observable, this will be like shoving the outcomes around. So what is now nice is that for each observable A in the system algebra, there is an R relational observable which you can get by sort of twisting with this quantum reference frame. And this is called the relativization map. Kasia gave an example of this in a slightly different setting, but this is why I want to integrate. I integrate sort of the translations, if you like, of my system observable with the measure given by this quantum reference frame. And you can, if you like to think in this conditional sense, so I take some reference state, then this is basically just the integral of translations of this observable with some probability distribution of my group. Now, what is a very nice result is if you have a sufficiently nice frame observable, I won't go into details what I mean here, then there exists some sequence of states that gives you, in a sense, the delta distribution on your group. So what we can get from this is what I will refer to as a localization theorem, and I've rephrased it here slightly, but essentially this result is from this paper of Karet, Glowatsky, and Loveridge, which is if you have a sufficiently nice reference algebra, each observable in A can be approximated by these conditional A-relational observables. So you can get back essentially all the statistics of your system algebra from these relational observables, as long as your reference frame is, in a sense, sufficiently large. Okay, some brief comments about this distinction between relational and what sometimes is called bare observables of your system. So, of course, there are many ways to model a system, both in a quantum or classical sense. But one such choice one can make is one takes relational or one takes these bare observables. So relational were invariant under some symmetry, which one can maybe view as a redundancy in your description, but it relies on some concrete external reference frame, some other quantum system, to really access the physical content of your model. Now, the bare observables are observables only involving the system of interest, possibly breaking some symmetries, and they arise from these relational observables by conditioning on this reference frame, assuming it can be arbitrarily localized. And therefore, I think one way of viewing this is that the bare observables are some kind of idealization, this description of this relational perspective. Now, idealizations in mathematical physics are all abound, but this is one of them, which I think is an interesting one, because this distinction matters to some extent, because this algebra of bare observables and this algebra of relational observables may have very different algebraic structure. And this is something we investigated in this paper. And one particular application of this is that in quantum field theory, it's pretty difficult to assign entropies to algebras, because basically there's always an infinite amount of entanglement entropy. But if you restrict yourself to these relational algebras, it seems that you can sometimes get some kind of regularized notion of entropy, which people in quantum gravity are pretty excited about. So, so that is one reason why one would care about this distinction. Now, how do you actually how do you measure these relational observables? I'm going to, how much time do I have, by the way? 10 minutes. Okay, good. Sorry? Okay. I'll hurry up. So I will basically sketch what I mean by a measurement scheme, but in this abstract von Neumann algebra setting, and I'm going to do something slightly more general than the Fewster and Verch, or let's say the Bush-Pelompa Lati Yenen description, which is I have von Neumann algebra. I want to measure an observable A in my system algebra. I have a von Neumann algebra, which I will treat as probe. There's some state on my probe preparation, and this theta is some kind of encoding the interaction between the system and the probe, but instead of an automorphism, as Chris was discussing, I will use a unital completely positive map. And this is essentially a generalization, and what you should think about is I allow for some kind of uncertainty in what interaction I'm going to do. So say I take one automorphism and I take another, and I take their convex combination, I will end up with a unital completely positive map. You can think of this, okay, depending on a coin flip, I'm going to press this button or that button to do my measurement. Roughly speaking, quantum circuits representations of this, but that's not really the way I was taught, so this is what I'm sticking to. Now, state update, Chris also talked about this. So putting these theta, b's, and observables in your system and states in your system together in this way gives you some way to talk about state updates. So recall this observable b took in, let's say, subsets of your sample space, so you can condition on your outcome of your measurement being in that sample space. And if this, basically this, if there is any probability of this measurement happening, which this statement comes down to, then you can define an updated state sort of conditioned on that outcome, which you can write in this way. Okay, now, as I mentioned, there are group actions around, so A and now B are these W star dynamical systems, or W star G algebras. And that means that you can also transform your measurement scheme around. So you can transform your state in some way, your probe state in some way, you can transform your system state in some way, you can transform your probe observable in some way, and then stringing these together gives you a measurement scheme for, well, unsurprisingly, the transformed system observable. So moving around the measurement scheme moves around the observable that you measure, unsurprisingly perhaps. Now recall that, well, we took this perspective that actually we're interested in these relational observables, which are somehow labeled by a reference state rho or given by an invariant. Can we construct a notion of, let's say, measurement schemes labeled by such a state rho, such that they transform covariantly in this way and measure this A rho? Now, a first attempt is perhaps to say, well, sigma is a state that has a convex structure. Because I was talking about these unital completely positive maps, they have a convex structure. Of course, observables have a convex structure. So I can talk about mixing. So I could try, okay, well, this triple, I can like take a sort of direct sum of them in a way. So I can say, oh, this should be convex linear. I should say, okay, this should be covariant transforming in a way. There should be some continuity requirement, which I will discuss. But the problem is then that this combination fails to be convex linear in general. So basically, because I'm taking products of convex linear things, the observable that I measure will not depend convexly on the probe, on the reference state. So a slightly second attempt is that I will use a different reference system for each of my ingredients of my measurement scheme. So I have one for the probe state, one for the system state, one for the probe state, one for the interaction, and one for the probe observable, such that this is convex linear in each entry. Simple enough. Covariance still the same. Continuity one can nail down, which I will get to in a moment. And then one can define, well, this observable A depending on state rho 1, rho 2, and rho 3. Now, my proposition is that there exists a unique relational observable in the tensor product of these three reference frames. That is a relational observable that corresponds when you to this induced observable when you take a state that factors over these three sort of different reference algebras. Now, one way to construct this is to construct, let's say, the analog of the invariant observable in my reference algebra for this state and this interaction. So what one can show is that there is a unique, completely possible equivariant, so that is sort of the closest we can get for invariance, for maps, if you like, map from your algebra B into your reference frame, your first reference frame, which will be the, let's say, relational analog of our probe state, and a unique, completely positive equivariant map from our system and probe algebra into our system, probe, and reference algebra, such that, well, you get this conditioned in a sort of obvious, from these in an obvious way. The continuity conditions can essentially be read off from these. You say, okay, if I want this to be an equivariant map from B to R, then that gives certain continuity conditions on how sigma should depend continuously on rho, in some sense. Okay. Now, the relational observable in R1, R2, R3, and you now just get by stringing them together in the same way as before. But we have some extra identities for these reference frames thrown in at various points. Now, some observations. We can interpret this sigma tilde as some kind of state preparation protocol, and theta as some controlled interaction between A and B, which are now controlled by these reference algebras. I should point out, alpha tilde rho is also meaningful, so it's related to these to these measurement schemes when rho is a product state, but it's also meaningful when rho is no product state. So we can interpret this as the outcome of a measurement where the control parameters for all of your steps in your measurement scheme are somehow entangled or correlated or even entangled. The induced observable still makes sense. And there's some similarities which I still have to understand fully with some notion of relational operations, which are, well, were discussed in a talk which I saw last week, but the paper is still to appear, so I have to dig this out. But I did want to mention them at this point, which is related to the Wigner-Araki-Yanase theorem. But anyway, now one can also do state updates relationally in this. Okay, I really have to hurry up. Which is basically exactly the same as we were doing before, but now instead of just entering a system state, we also have to enter this reference state. And you can talk about state updates now conditioned on the outcome, but also the reference state, if well defined, and otherwise if this probability is non-zero. And again, this conditional state update makes sense and transforms covariantly in a certain way, in a way that updating the state with a sort of translated measurement is the same as translating your state, doing a measurement, translating back. Okay. Also, this makes sense for rho being some kind of mixture. So also here we can do this. Now, some basically quick examples. Similarly to this relativization, one can construct some notion of relativized states, interactions, and probe observables. One can string together these, and you get this as an induced observable, which depends on these three reference frames. Now we can again use this localization result of Karet-Loatsky and Loveridge to conclude that for each observable A with a measurement scheme, or each observable and measurement scheme for that observable, there exists an R-relational measurement scheme for the observable, for the R-relational observable A, and a sequence of states rho and such that the induced observable, such that you can approximate this unrelational observable by these induced system observables, and the same can be done for the probe state. So also the probe state, the system state update can be approximated by relational system state updates. Now, I'm out of time, so I will just say something very briefly. Can we implement such relational schemes in QFT in the setting of, for instance, Fewster and Ver? Yes, but this is work in progress. There's a sort of cheating way where you introduce some very weird quantum fields that are not expected to be physical in any way. So we want to have more realistic examples, which is work in progress, with that also Benito mentioned, I believe. Okay, and even one can try to go on from there. Can we talk about measurement schemes in a completely locally covariant way on the measurements happening in all space-time, sort of in the same description? There I would like to end. Thank you very much.
I think we have time for one question from the audience.
Thanks very much, Dan. That was really interesting. In what sense does a reference algebra being sufficiently nice? Like, how do I know if I'm dealing with a reference algebra that is insufficiently
so there is
nice?
There's a technical statement, which is that, so I discussed this positive operator valued measure that transforms nicely into this group structure. It is this, your reference algebra, if it is sufficiently nice, if A, it admits such an observable, this is a non-trivial requirement, and this observable satisfies what is known as the norm 1 property. So, for instance, if projection valued, this works. If it's not projection valued, you can still ask, okay, but are these operators somehow norm 1, meaning they have the same sort of norm as a projection? Where this doesn't work, for instance, is if you have a compact group, you can just do sort of averaging with respect to the group, and all your states are just going to be sort of uniform distributions on this, given uniform distributions on this group, which you will never be able to localize, of course, because uniform will never approximate a delta function. But this norm 1 property gives you some. Then these exist, and what you should think of, for instance, is that you have sufficiently many states in your, sufficiently many sort of distinguished states in your reference algebra. I don't know if that's a very satisfying answer, but there's a technical condition that we can write out.
Okay, I think we should postpone further questions for Dan to the coffee break, and let's thank him very much again.
Sorry for being slightly over time.
Yes. How do I
Should I take that one? Okay, so let's move on. Last talk before the coffee break. I think we are on the same line of research of the previous 2 talks, because the next speaker is going to be Filippo Nava. He's a PhD here in York, and he's going to tell us about gluing in electromagnetism, a differential cohomology approach.
Thank you very much, Stefano. First I would like to thank you all for coming on this very hot day, and also to the audience online, and also thanks to Rick for setting up this nice, helping this, setting this event. So yeah, today I would like to talk about some ongoing work for my PhD with my supervisor Kasia and Daan. And there will be some overlap with the previous talks indeed. So I would like to talk about this gluing problem. But first I want to give a bit of a motivation for this work. So the main focus in this talk would be that gauge theories, that are theories of nature, are very interesting both from the physical perspective but also from a mathematical perspective. And indeed, gauge theory exhibits some very interesting topological effects that I would like to talk to you about a bit today. And in particular, if you study a gauge theory on a space-time with also a boundary, as we have seen in Kasia's talk, it's really important to take into account some additional degrees of freedom. These are known as edge modes that were introduced by Donnelly and Friedel in this work. And it's really important to take these degrees of freedom into account for many reasons. For instance, as we have seen, you can define a quantum reference frame out of it. And also there are computations that shows that, for instance, these degrees of freedom has a contribution on entanglement entropy. So it's important to take these into account. We have seen that there has been some effort in the HEFT community to incorporate these effects in the HEFT setting. So the plan for my talk is indeed start by explaining what I mean by topological effects and providing some example in a very simple theory, that is electromagnetism, that still is very rich from the topological perspective. Then I want to introduce the problem I want to study, that I like to call the cutting and gluing problem. And after that, I will need to introduce the framework that we are using for dealing with this problem, that of relative differential cohomology. And in the end, I will present a theorem that actually solves the problem. Okay, so some assumptions and notation. So in this talk with the space-time, I will mean always Lorentzian manifold, and I assume the manifold to have a time-like boundary. I will also focus on dimension 4. And then I will talk a lot about some topological objects. These are all groups. I will talk about chains, cycles, and homology. So these are fancy names for naming things that are very intuitive. And for instance, for chains, you can think of a K-chain as some geometric object living in space-time. So for instance, in degree 2, you can have in mind the example of a two-dimensional surface. Or in degree 1, you can think of a line in space, in degree 0 as points, etc. Now for cycles, these are defined simply by chains with an empty boundary. So for instance, in degree 2, if we consider a closed surface, this has an empty boundary, or in degree 1, a closed loop in space-time. And finally, homology, again, is a topological way to capture the fact that in some spaces, we may have cycles that are not contractible. Indeed, in this room, for instance, if I draw a sphere, I can always collapse the sphere to a point. So you see, you can take a sphere and you can collapse, but for instance, if you remove a point from this room, for example, there will be spheres that cannot be contracted because I removed this blue point. And this is a phenomenon captured by the second homology group. In the same way, the first homology captured the fact that we may have loops that are not contractible. For instance, if you remove now a line, for example, this line in blue, the loops that encircle this line will not be contractible. So this is what homology is capturing. So as promised, I want to give some examples of where there is a very nice interplay between topology and electromagnetism. And a very well-known example is the Aronoff-Bohm effect. So here I included the original paper by Aronoff and Bohm, 1959, named The Significance of Electric Potentials in the Quantum Theory. So in this paper, the authors, they write also in the abstract, they discuss some interesting properties of electromagnetic potentials in the quantum domain. And they show that there exist effects of potentials on charged particles, even in the region where all the fields vanish. Now, I want to explain a bit what is the setup for this experiment and motivate why topology has a role. And in particular, the role is of the first homology group of this space. So, grounded in the experiments, what is the setup? So it's very simple. You consider a solenoid, a very long solenoid indeed, so that when you apply a current in the solenoid, inside the solenoid you get a magnetic field, but outside of the solenoid there is no magnetic field. That's very important. Then you take a double slit, so that there are two slits here, and you send an electron on this double slit. And we know from quantum mechanics that if you do these many times, in the end, behind the double slits, you will observe an interference pattern. Now, what's interesting is that all the electrons are traveling in a space with no magnetic field, but you can observe a shift to the left or to the right of this interference pattern, depending on the fact that there is a magnetic field inside of the solenoid or not. So that's very interesting, it's very odd. and it's also something that in the 80s was observed, so it's a well-established piece of physics. And the where topology enters, is the fact that we are considering a space where there are loops that are not contractible. So indeed, these loops that goes around these very long solenoid are not fully contractible. And in a sense, the electrons are able to capture this feature of this space. That's a very, very interesting effect. I want also to talk about something a bit more abstract and not well established, at least in experiments, but it's still very interesting where topology enters. And this is the case of torsion. So when the homology of our space has a torsion. This is a kind of abstract notion, but I can give you some intuition of what I mean. So when we have an abelian group, we can define the torsion component of this abelian group. Roughly speaking, this is a subgroup such that the elements of the subgroup are idempotent. So you take the n exponent of an element, you get the identity. And a simple example of such of a space whose homology has torsion is the so-called Klein bottle. So this is, here I represent a diagram for the Klein bottle. You can construct a Klein bottle by taking a square and gluing these two sides and these two sides with opposite orientation. And you can see by an heuristic argument that if you take the sum of two loops in this space, you can start contracting these loops, and you contract, and you get a loop in the back that then is fully contractible. So this space, this captures the fact that this space has a torsion in its homology. Now, why do we care about this? Well, because recently there appeared a paper by Fried, Moore, and Segal, known as, whose title is The Uncertainty of Fluxes. And you can read from the abstract that the authors considered ordinary quantum Maxwell theory for a free electromagnetic field, and they observed that the magnetic and electric fluxes cannot be simultaneously measured. And this uncertainty principle reflects torsion. So what they observe in the paper is a consequence of studying electromagnetism on a space with torsion. Very good. So we have seen that topology plays a really interesting role even in such a simple theory. And now we want to move to the main problem in this talk, that is this cutting and gluing problem. So I'm very happy that we have heard experts actually in the field of AQFT that explained us all the beauties of this approach. So to the bare minimum, an AQFT we have learned today, it's the idea of assigning to a spacetime an algebra of observables. Now, if we consider a spacetime, generic spacetime with some non-trivial topology, as we have seen, we can encounter many topological effects. So one could say, well, what about working in a simpler partition of this spacetime? So I can consider cutting this spacetime, so considering some small subregions, and I think of some experimentalists living in this partition. So all the experimentalists have access to observables in the partition. And now the question is, well, how can we reconstruct the full algebra of observables on the global spacetime, starting from these individual perspectives, if you want, in these small subregions? So that's the problem I want to discuss today. And in order to do so, I need to introduce the framework we are using and try to convince you that it's beautiful also on its own, that it is relative differential cohomology. Okay, so now we are working on a spacetime with a non-empty boundary. And I need to relax a bit the notion of chain that I was presenting to you before. So I was saying chain is a surface or a line in spacetime. Now I want to relativize this construction relative to the boundary. So I need to define what is a relative chain. that's very simple. It's simply a pair of a k-chain living in the bulk of spacetime and some data, k-1 chain, on the boundary. So for example, a relative 1 chain is given by these red and blue dots. 1 line in the bulk and 2 endpoints on the boundary. And this comes with a definition of a suitable boundary map so that we can discuss what is a relative cycle. So a relative cycle is something with empty boundary. And looking at the definition of this boundary map, we can see that this object that I'm drawing is indeed a relative cycle. Indeed, if you take the boundary of the red loop, you get the 2 endpoints, and if you choose the orientation accordingly, you sum the 2 loop points, you get 0. And in the same way, you take the boundary of a point, that's 0, that's a relative cycle. So I'm generalizing the idea of cycle. These are not only loops in spacetime, but also lines attached to the boundary. And now what can we integrate on such an object? Well, a relative differential form. That's simply a pair of a k form in the bulk and a k-1 form on the boundary. Okay, so I'm ready to introduce the main protagonist in this talk, that is the space of relative differential characters. This is a definition by Chigre and Simons. So a relative differential character, H, is a homomorphism from the space of relative 1 cycles into U1, so that we are assigning to loops in spacetime a U1 phase, but also to lines attached to the boundary, again a U1 phase. And this comes equipped with 2 forms, so a relative 2 form, F and alpha, in such a way that if you evaluate the character on the boundary of a chain, like this object, what you have to do is simply integrating F and the alpha on the corresponding components. Now, the physical intuition of this object is that if you imagine an electron traveling on a path, we want to think of the character as the U1 phase that the wave function of the electron acquires when traveling on this path. So this is the physical intuition behind this definition. So a simple example I can provide of a differential character, if I choose a 1 form in spacetime and a 0 form on the boundary, I can construct what is called a topologically trivial character. So that's iota of A and phi. What I do, simply I integrate A on the bulk component, and I multiply by e to the plus or minus I phi at the endpoints. Okay? That's a simple definition, but I want to stress that not all differential characters are topologically trivial. And indeed, here's a very complicated and abstract diagram that tries to capture this idea. Here we have differential characters, and this map as I'm describing is this object here, but we have a more structure, a lot of structure, that I simplify with this pictorial diagram to highlight that with these gadgets, these differential characters, we can discuss any topological effects in electromagnetism. So you see that we can discuss, for instance, the Aharonov-Bohm effect, monopause, and even torsion. So it's a very rich object to study. Okay, now I'm ready to define the classical theory. So what we mean by classical theory is a set of classical fields that are relative differential characters. And to discuss the dynamics, we choose to study an action of this form. And in particular, if you look just at the bulk component, that's basically the Faraday-Maxwell action. Now, taking a variation, the Euler-Lagrange equation of this action are the following. So you see in the bulk of spacetime, you get the Maxwell equation for F, plus some dynamics for this new object alpha, and this comes equipped with a sort of boundary condition between these 2 data. So this is the dynamics we get. Okay, now I'm finally ready to define what I mean by an observable for such a theory. And then we can come to the gluing result. Okay, first let me start from the case without boundary. So we consider A gauge field. Now, if we choose a 3-form with compact support that is closed, we can define a sort of smeared Wilson loop observable, something that Kasia was telling us before, some sort of object that is not singular as something living on a loop, but some smeared kind of object. And we can do the same in the relative case. So we can define a sort of smeared Wilson line observable by smearing also this component on the boundary phi with the pullback of the 3-form. So you get some sort of Wilson line attached to the boundary. But now, as I told you before, not all differential characters are topologically trivial. So we need to employ some heavy gadgets. Luckily, in a paper by Baker, Benini, Schenkel, and Salzburg, the authors introduced a nice object that is a Pontryagin pairing. I don't want to enter too much in the details, but basically this is a pairing that takes a differential character and it pairs with another object to get a U1 phase. And this other object is, again, a space of differential characters, but of higher degree and with compact support. So it's a bit of a complicated object, but in our work we were able to extend this pairing also to the relative case, so getting a sort of relative Pontryagin pairing. Now, what are the observables for this system? So we define the generators W as this Pontryagin dual object, and finally the free-star algebra of observables, sorry, the algebra of observables A is defined as the free-star algebras on the complex numbers generated by these W. So this is getting a bit intricate, I realize. The take-home message is that now also observables are modeled by differential characters. So they carry a rich topological structure in a sense. And finally, I can come to the main result of this talk, that is a gluing theorem. So as I was telling to you before, consider a space-time and consider space-time partitioned into subregions M1 and M2. Now, if we look at the space of compatible observables, so think of these as some, for example, smeared Wilson lines that match smoothly at the gluing interface, then if we choose the cutting interface in a good way, so we need to ask that that's a technical condition, the second cohomology group of the gluing interface is trivial, but with this choice, we're able to prove that there exists a surjective gluing map that reconstruct the generators on the full space-time from the generators on the partition. That's a positive answer to the gluing problem. It's possible to generate the algebra of observables on the global space-time from the localized pieces, in a sense. Now, because this is a quantum information, relativistic quantum information conference, I want to spend a few words on the quantization of the system. That is quite straightforward in a sense. So what we do is constructing a Poisson bracket structure to define the classical dynamics, and then the quantum algebra of observables is obtained by taking the Weil C-star algebra generated by W. So the idea is that we take the commutative product of classical observables and we deform this product introducing an object H bar in such a way that this product is non-commutative. And so that if we look at the commutator of observables, at first order in H bar, we get the usual Dirac quantization prescription. This convinces you that this is a quantization of the model in a sense. And just a feature, a technicality, but for those interested in the AQFT framework, the algebra that we obtain has a non-trivial center. So there are elements, generators, that commute with all the other generators. So that's a feature of the algebra we obtain. And with this, I want to conclude. So I told you about the interesting features of electromagnetism. It's a simple theory, but still exhibit a really rich topological structure. And a very useful tool, I think, is to capture these effects is the framework of relative differential cohomology. And in the end, I showed you a gluing theorem that allows to, in a sense, reconstruct the global physics starting from local algebras. So some future avenues that I included, there are many possible things one could want to study. For instance, could tackle the problem from a measurement perspective. So how do we measure, as Dan was telling us, these observables? I think it would be really interesting to look at the Harnaut-Bohm effect, but from a quantum perspective. So the example I was showing to you before, it's a setup where we're using a quantum probe, so an electron, but the background, in a sense, the electromagnetic background is classical. So one could think that maybe it's possible, maybe it's something that we can also measure, it's possible to induce a quantum superposition of the state of the electromagnetic field as well in a sort of quantum superposition of Harnaut-Bohm phases. And I want to spend just a few words on this last point. Topological effects in quantum mechanics and quantum field theory are also really interesting from a topological quantum error correction perspective. So I'm not an expert in these, but the idea of this type of construction is that if you're able to construct a state that is topological in some sense, then this state is very robust under external influence of other systems. So it's a system that, for example, can hold coherence, that is a really important feature in quantum information, for a longer time. So I think this maybe is something that could be looked also for theories electromagnetism. And with this, I want to thank you all for the attention, and I'm happy to take questions.
I think we have time for one question, certainly, and then let's see how we are doing.
I don't know the answer. It's an actual question. So there are these ideas with generalized symmetries floating around, and it's particularly used in like condensed matter physics, where you also have boundaries, corners, and so on. So do you think that your formalism generalizes?
Yes, thanks for the question. Indeed, I can show you a backup slide on this. It was not arranged. It's something that thinking a bit of exploring. Indeed, as Kasia was pointing out, there is a famous construction due to Gayot and collaborators on understanding higher symmetries, in a sense, given by higher form symmetries, and these may be related to things that Kasia was pointing out. And indeed, in this framework, I think it's something that is really natural to discuss. Maybe I don't want to enter too much in the details, but basically, these our system, also the classical level, has some interesting symmetries that we call the flat symmetries. And when looking only at the bulk, these flat symmetries basically are one-form symmetries, the one that Gayot and collaborators are observing in their paper. But now, so my slide is a bit cut, there was a third line. Because we have a boundary, we also have some symmetries related to just the boundary component, but also some maybe relative one-form symmetry, so symmetries that has an interplay between the bulk and the boundary component. This is really preliminary. There's work to be done, but I think is definitely something that is has a natural description in this language.
Okay, so I think if there are further questions, we will ask Filippo in the coffee break, and let's thank him very much again. So we reconvene at 4:30 UK time, so 25 minutes.
Okay, you can start again. Now we will have a talk, online talk by Lawrence Walleghem, PhD here in York, that will talk about the Wegener's friend black hole adventure. So please, Lawrence, when you're ready.
Yes, thank you very much for this nice introduction, and thank you very much for this invitation to speak here. And I'm sorry I can't be there in person. Thank you for organizing this wonderful conference. So I will talk about Wegener's friends and black holes today. And please interrupt me at all times to ask questions and so on. So the work I will present is based on these papers here with my co-authors Rui, Matt, Stefan, Ila, David, Rafa, and Lorenzo. So the outline for today. We all know the strange feature of quantum mechanics that systems behave differently when observed and not observed. But then we can ask ourselves the question, what if we observe the observer? Well, one scenario probing this question is that of Wegener's friends, closely related in spirit to Schrödinger's cat. So in Wegener's friend scenario, we have Wegener and a friend, and the friend resides inside a sealed lab and performs the measurements. Wegener, who remains outside the sealed lab, considers his friend as ultimately being a quantum system as well, and describes the evolution of this closed system as a unitary. So after the friend's measurements, Wegener argues that the friend is in a superposition of seeing different outcomes at odds with the claim of the friend who claims to see a single valued outcome. And extended Wegener's friend paradoxes, such as the FR paradox or the Frasiger-Renner paradox, they combine several such Wegeners and friends, and they present us with questions such as, can quantum theory describe the use of itself consistently? Are events absolute? And so on. And central to both Wegener's friends and black hole puzzles lies the question of unitarity. And I
Can you communicate with him? Yeah, I would call him.
Apologies for the technical disruptions.
continue.
Yes, Yes, please.
Okay, apologies. I think it was my internet that suddenly failed. So, yes, so today I will combine Wigner's friend and black holes. And yeah, I will end with a short discussion, and I will particularly discuss some of the assumptions of black hole puzzles and potential problems with it. So the refined version of the FR paradox goes as follows. We have two friends, Alice and Bob, who reside in sealed labs, and they hold entangled systems upon which they will perform measurements. They have super observers, Ursula and Wigner. So these super observers are observers who have quantum control over everything in the lab of their friend. So for example, Ursula has quantum control over all the degrees of freedom in or all relevant degrees of freedom in Alice's lab. So, and same for Wigner and Bob. And Alice and Bob, they share a hardy entangled state, and they perform a Z measurement on their system. So measurement in the computational basis. And next, Ursula and Wigner, they model this measurement unitarily, as they just consider Alice and Bob to be ordinary quantum systems and describe the evolution of these sealed labs as a unitary. So next, Ursula and Wigner, they apply the inverse unitary of these unitaries that describe the measurements, and they perform a next measurement on the systems that Alice and Bob were holding. And next, Ursula and Wigner, they make predictions for Bob and Alice, respectively. And in some rounds of the protocol, Ursula will find that Bob should obtain 1, and Wigner will find that Alice will obtain 0. But when they meet and they compare their predictions, they find that Alice should obtain 1 and Bob should obtain 0. Alice should obtain 0 and Bob should obtain 1. But this is a correlation, this is a joint correlation that can never occur given the initial state. So there is a problem, there is a paradox. And so what does this paradox tell us? Well, it tells us we must refute one of the assumptions. And we have 3 main assumptions. First, that universality of quantum theory, that such super observers exist, so that observers can be modeled unitarily. Also, measurements that these observers performed can be modeled unitarily by certain other observers, which are called super observers. Secondly, absoluteness of observed events, that every performed measurement has an absolute single-valued outcome, and Born compatibility, which requires that these outcome assignments are compatible with the agent's use of the Born rule. And in fact, we can weaken absoluteness to a weaker conjunction of 2 assumptions, but I won't go into detail here. And so to resolve the paradox, we must give up on one of the assumptions. And the one I want to talk a bit more about here is giving up on absoluteness. So what if we give up on absoluteness? Well, it means we must replace absoluteness of observed events with another principle that allows agents to make predictions and so on. And in this case, our paradox becomes particularly interesting because it suggests a replacing principle, which we call the relativity of observed events, that every performed measurement can be assigned a single valued outcome by an agent who learns about that outcome. Or put in a slogan that extends Perche's dictum, unperformed measurements have no results and unknown results have no values. And in fact, one can argue that one should apply this principle also to interventions or free choices, in which case one gets a generalized version of this relativity. So let's move to black holes, and I will start by briefly recapping the black hole information puzzle. So on the right here, we see we have a Penrose diagram of a collapsing star, which next evaporates through Hawking radiation. And at the end, one is left with only radiation. So Hawking suggested that the radiation is purely thermal, so that it doesn't contain a lot of quantum information. So the question is, if we are left with only radiation after the black hole evaporates, where did the information go? Where did the information about the initial states of collapsing matter go? If we started from a pure state of collapsing matter, where are the quantum correlations after evaporation? And in fact, well, by now there's, I think most of the people in this field believe that there is actually unitarity and that we can recover all the information, but how exactly is not well known. And until that point, it remains of course possible that there is no unitarity. But now, if one expects unitarity, there is a famous argument for how the information might leak out in an abstract model, or how the entropy over time should look like. So according to, if we start from a pure state of collapsing matter and we start with zero radiation, the entropy of the radiation starts at zero. At zero time, entropy starts at zero. And then according to Hawking's calculation, as more and more radiation gets emitted, the entropy increases until it's fully evaporated and it flattens out. Now, Page gave a general argument of how a unitary curve might look like. So he based himself on an abstract toy model where unitarity was built into the assumptions. And he argued that at some point, or his calculations showed that at some point, the entropy curve goes down again, and meaning that late time radiation purifies the early radiation. And the unitarity could be restored in this way. Now, if we believe that the Page curve is a correct argument for how the entropy curve might look like, there is another paradox, which is called the firewall paradox. And according to the Page curve, the late time radiation purifies the early radiation. So meaning the late time radiation should be highly entangled with the early radiation. However, according to quantum field theory on curved spacetime, there's high entanglement across the horizon, and modes just inside the horizon should be highly entangled with modes just outside the horizon. If one identifies these modes just outside the horizon with late time radiation, one gets a paradox because, or one gets a contradiction, because the late time radiation should be highly entangled with the early radiation and with the modes inside, leading to a violation of monogamy of entanglements. So here I should note that there are many subtleties which we will come back to. And next, let's combine this with Wigner's friend. So let's combine black hole puzzles with Wigner's friend. First, I should say that we provisionally adopt standard assumptions in black hole puzzles, such as the cloning and firewall paradox, which includes the existence of suitable black hole radiation subsystems, the possibility of decoding them in required space-time region, an approximate inside-outside factorization, and the identification of late radiation with near horizon modes. And these assumptions are not derived here. I don't think they're really derived anywhere properly yet. And they are in fact known to be actually very delicate in quantum gravity. So the no-go results here should be read as conditional results, assuming these, while assuming these assumptions. So I will come back to critically assessing these assumptions and in fact seriously question them later. So if we combine Wigner's friend and black holes, we get the following. So we start with Alice and Bob, two friends in sealed labs who will fall into a black hole. And I should say that our paradox, our scenario combines the black hole cloning paradox with extended Wigner's friend arguments, and one can do the same for the firewall paradox, but I won't present this here. So we have Alice and Bob, two friends residing in sealed labs who share a Hardy entangled state. And Alice and Bob will measure their systems in the Z basis, in the computational basis, and they will fall into the black hole. Next, Ursula and Wigner, they remain outside the black hole. They catch the Hawking radiation coming from Alice's and Bob's labs, and they decode the initial states, undo the measurement, and measure their systems in the X basis. And next, Ursula and Wigner, they reason about the outcomes of Alice and Bob inside the black hole, and they obtain a contradiction. Just as in the FR. So the contradiction they obtain is just in the same way as in the FR. So Wigner reasons about Alice, for example, Ursula about Bob, and they find a contradiction. So what are the implications? What does this paradox tell us? Well, it seems that the outcomes of Alice and Bob and Ursula and Wigner, perhaps in a naive space-time diagram, are all available on a single spatial slice. So one can argue that they should indeed satisfy the Born rule, meaning that Ursula's and Wigner's predictions are indeed correct, and one derives a contradiction. But as we will see, this space-time diagram and the use of the spatial slice might be problematic or might have many subtleties. So we can go to a second no-go theorem, and which state that if such a super observer outside the black hole can obtain and decode the Hawking radiation encoding the sealed lab state of an observer who fell into the black hole, we have a contradiction between the following three assumptions. So first, that the outcome records of Alice and Bob inside the black hole remain coherent and untouched. Secondly, that observers can make Born rule predictions about such measurement outcomes, and that observers who can communicate and meet have to agree on their predictions. So what do these new scenarios contribute? Well, the firewall and cloning paradox, they leave room for some theory to describe the interior and the exterior and evade the no-go theorems. And this is as the contradiction is within the formalism itself only. So there is a contradiction with monogamy of entanglement, or there is a contradiction with no cloning, and this is a contradiction within the formalism only. Now, the contradiction that we find is shows that no such theory can exist if it has to give the predictions of quantum theory. So we find a contradiction not on the level within the formalism, but we find a contradiction on the level of the predictions of quantum theory for correlations. So what should we do about this contradiction? Well, we should carefully reassess assumptions, of course, and look at where problems might arise. And in the first no-go theorem, there might be this problem with single spatial slice and so on, and the space-time diagram. So let's move to the second no-go theorem and see where problems could arise there. And here I highlighted some things in red that might be problematic. Right, so if we say obtain and decode the Hawking radiation, where can we decode this radiation? How can we do this? And if we talk about outcome records inside the black hole, the question is, what is the meaning of inside the black hole? What is the operational meaning? What is the correct causal structure? And same if we say that these insides records remain untouched, what observables are we talking about? What operators are we talking about? So many questions. And one could argue that it is indeed this first assumption here which is problematic, that the outcome records of Alice and Bob inside the black hole remain coherent and untouched. But at first this might seem strange, because if we look back at this space-time diagram, we should say, okay, Alice and Bob's outcome records are very far from or space-like separated in this perhaps naive picture from Ursula and Wigner's operations. So is this a violation of no signaling, or what do we have? So, and one can perhaps argue that this suggests that maybe the inside and the outside, the inside and the radiation outside the black hole that we are talking about are maybe not distinct degrees of freedom. So this might seem strange at first, but there's many subtleties which might make this more plausible, which we will come back to in a minute. So I will start by briefly recapping proposed answers to the black hole information puzzle in literature. So there's arguments that there is true information loss. There's argued that remnants, small objects at the end of evaporation, hold the information for a very long time or indefinitely. And there's a possibility that that Hawking's calculations missed something, or that modifications are required. And these modifications, there's proposals for violent modifications, non-violent modifications, or there's the possibility that other aspects were missed. And rather than already assuming many more things, let's first look at the assumptions and see where subtleties within the current formalisms are already there. So first, according to conservation laws, also those related to soft hair and so on, by quantum gravitational back reaction, one could expect the bulk to be highly superposed at some point, to consist of highly superposed geometries. So if one then talks, for example, about infalling observers or infalling radiation or so on, there's a possibility that these observers get entangled with the geometry or even measure it or so on. Secondly, there's the issue of locality and gauge invariance, and a related issue of how to define the black hole degrees of freedom and the radiation degrees of freedom. So if one has gauge invariance, the notion of locality is non-trivial, and one can work with relational or dressed observables and so on, but these might tweak with the locality, with the commuting of space-like separated observables, for example. And related to this, there's a question of where the information recovery happens, and how and where should we expect the page curve from the radiation. So should we expect it still deep into the bulk? Perhaps not, because there one can cause non-trivial back reaction. One has the difficulties of defining what these operators are in the bulk of the spacetime, inside, outside factorizations, definition of radiation, and so on. So perhaps it's wrong to really expect that one can recover the information by easy operations inside the bulk. And this relates, of course, to the question of what is the correct causal structure of the spacetime. There's further subtleties regarding the firewall argument. So one invokes high entanglement across the horizon.
5 minutes left, Lawrence.
Sorry, yeah?
You have 5 minutes left.
Sorry? 5 minutes. Okay. Sorry, yes. I didn't understand. Yes. So there's, regarding the firewall arguments, there's further subtleties, observer dependency of the entanglement, and also entanglement in a single space-time is invoked, high entanglement across the horizon there, but in a superposed space-time, we have, of course, a problem. And finally, there's potential back reaction by the infaller, and the question of specifying initial quantum states for black hole formation. And so one can argue that all these, if we relate back to our Nagot theorems, one can argue that these issues really make that this first assumption there is incorrect, which builds strongly builds on the or which already assumes these standard black hole assumptions. And so here we have the different subtleties and what they mean for the cloning paradox and our presented paradox, and for the firewall paradox, which I haven't presented here, or our extension of it. So yes, I won't go into further detail here, and I'll gladly answer any questions if there are any. So thank you for your attention, and yes, gladly take any questions.
Are there questions? Okay, if there are no questions, yeah.
Hey, Lawrence, thank you for the nice talk. I was wondering if you have considered if you are aware of the notion of partner systems and how they can be used to tell you some things about entanglement distribution in this kind of systems. Is this something you could use?
Yes, I think so. This is something one could definitely use here. Yes, one can try to make some assumptions regarding the entanglement, perhaps more precise regarding the partner modes. And I think eventually, if one wants to consider the problem more completely, then I think one needs to in some way define partner modes, but in superposed spacetimes or so on, or in really quantum spacetimes. So but this is something I haven't done. So yes, but thank you for the question and suggestion. It's very nice. Yes.
Thank you. Yeah, there is another question. So this is perhaps just because I don't really know how essentially my question is, in what formalism exactly have you been looking at this question? Because that wasn't entirely clear from my talk, because you wrote down Hilbert spaces, tensor products of them. This quantum field theory problematic, although one can probably get around them, but still at some point you were mentioning, okay, this is a problem of the formalism, this problem is sort of formal, or this thing is formalism independent, but what exactly is the setting in which you have looked at these paradoxes now? Because I didn't quite understand what you meant by the formalism and things like that.
Yeah. So there, by the formalism, I just mean the formalism of quantum theory. So and I consider quantum field theory also as an example of a quantum theory. So that's what I meant by the formalism there, and then it's assumed that there are approximate systems that Alice and Bob and so hold, that they can describe by in some approximation by quantum theory, while taking care of all the quantum field and quantum gravity things that happen in the background, or in which they basically move around. So yes, but I think people try to not take in these problems, when formulating these paradoxes, not take one specific approach and say, okay, we look at everything in this approach. But to resolve these paradoxes, of course, you need to make calculations. So you need to make appropriate choices of in which formalisms you can work, and in which formats you think it's you can formulate your assumptions and so on in a better way. So, and yes, and I think once one will do this, one will see which formalisms are there that one can use, which are not expressive enough for these problems, and also which assumptions are perhaps then the ones we should leave behind. So does that answer your question, or?
Yeah, I think so. I mean, when you said approximate things by quantum mechanics, do you mean say, okay, we approximate things by finite dimensional Hilbert spaces, some kind of coarse graining? Because I think this is what Page in like these Page curves argument also did. They apply these original derivations were all in sort of finite dimensional Hilbert space setting, and probably when you need to go to quantum field theory, you need to use relative entropy, blah blah blah. But because I didn't really see this in your talk, I was wondering to what extent these things rely on finite dimensions, or what things are completely general. I mean, perhaps I would just need to have a look at paper, of course, but maybe some thoughts.
Yes. So it's not that we resort to a specific finite dimensional example, such as Page was doing, right? He really just considered a specific toy model. That's not what we're doing here. We're basically saying, okay, we have a quantum theory which has these properties, which satisfies these assumptions, and then yes, whether that is finite, like whether that's an infinite dimensional system, or whether one says no, if one really looks at one quantizes all degrees of freedom, one has again a finite dimensional system or something, a finite dimensional Hilbert space or something. This is this is not something we go into detail here or something. So yes. Maybe that doesn't answer your question. I don't know.
Okay, I think we can postpone maybe this discussion after the conference. So let's thanks again, Lorenz.
Just with this, can you hear me? Yes. I think so. Shall I also take that? Rick, shall I also take this?
Okay, our next speaker is Stefano Galanda, a postdoc here in York, that will talk about modular theory and relative entropy. So please, Stefano, the floor is yours.
Okay, so thank you, Filippo. Thank you to the organizers for organizing this and to invite me to give a talk. So as it is already quite late, maybe let me say that I will keep the introduction very, at some point, formal and very easygoing. And I will like to tell you something about modular theory, how it is useful, a useful tool in understanding properties of local observables in algebraic QFT, and also properties of states. And in particular, how it is related to the notion of relative entropy. Okay, so we already heard many talks about AQFT. Indeed, we, as Chris said, we all somehow work on this topic here. So what I would like to add to this discussion now is to tell you how modular theory is a natural, let's say, or a very useful tool to understand maybe some more mathematical aspects of the theory, more, let's say, abstract properties of the theory that are anyway useful and nice, at least from a mathematical point of view. So the outline is as follows. So I will first give you a bit of introduction. We already had them, so I will try to be quick on that. Then I will connect these more abstract setting to what it is maybe more concrete, so boundary operators on a Hilbert space, namely von Neumann algebra, and tell you how the observables of QFT are mathematically different from those of quantum mechanics. This goes under the name of type 3 factors. And then I will introduce modular theory and tell you something about what one can do with that, and in particular connect with the notion of relative entropy in QFT. And then I will conclude with some remarks. While doing that, I will also mention some of my works. Indeed, also want to try to tell you something about what I'm doing. So more specifically, I will tell you something about a work that I've been doing together with Leonardo Sangaletti in Genova now, about a property of local algebras that is called Hug duality. And then I will tell you something about relative entropy, namely a work that I've been doing together with Albert Much and Rainer Wech about the, let's say, fermionic equivalent of coherent states. Okay, so let's start. One of the points from which I think the algebraic approach starts to be useful, or it becomes manifestly useful, is in the Stone-von Neumann theorem, at least from my point of view, which, of course, here I'm being a little bit formal, but essentially tells us that if I want to describe the states of a quantum theory, if my theory that I want to describe has finitely many degrees of freedom, then I can encode all the possible physical configurations, all the possible states inside a single Hilbert space. And this was also somehow solving the historical debate between Heisenberg and Schrödinger's picture of quantum mechanics. This is very nice, of course, it's a very important result. What happens, though, is that when we start considering systems which have infinitely many degrees of freedom, this theorem is not true anymore. Actually, this occurs already in systems of quantum statistical mechanics, such as infinite spin chains, but more importantly, especially for this talk, for systems in relativistic quantum field theory. In particular, in QFT, it happens also that not even just as states, so just as vectors in a Hilbert space, but it might even happen that two different states describing physically interesting situations are not even described by density matrices inside a single Hilbert space. And of course, this is something that you would like to be able to do, to compare different states, okay, which are physically interesting. So here is where the algebraic approach comes in, because it tries to put aside the Hilbert space description and derive it just as a second or a secondary notion. Indeed, the starting point, we already heard many times these Hag-Kastler axioms, so I can be a bit quicker on that. The starting point is to say, okay, I have a net of C-star algebras, essentially maps assigning to space-time regions algebras. Okay, here I wrote C-star, but as we saw in Kasia's talk, this can also be star algebras, which have to satisfy some nice axioms, physically motivated axioms, such as isotony or causality, namely commutation at space-like separation for these nets of algebra. One can also require covariance, namely if my space-time has some symmetry group, I would like this symmetry to be raised as an automorphism at the level of the algebras. And many more. So if you look into the literature, you might find more of these axioms. We saw also sometimes one puts the time slice as an axiom, and there are many others. But okay, for the sake of this talk, it's enough to list these three. And well, what is nice is that, okay, so far seems everything very abstract, but one can actually take this as a definition and try to say, okay, which kind of models satisfy this list of axioms? Well, there are many. For free theories, okay, one can construct Klein-Gordon, Dirac fields, Majorana, Maxwell, Proca, some gauge theories on any global hyperbolic spacetime. So I should I should make this comment here. This is a very nice framework, especially for describing QFT on curved spacetime. This is one of its strengths, actually. But also one can describe perturbatively interacting quantum field theories, so constructing perturbatively our star algebras of observables, which satisfy this list of axioms. So this is very nice. And ultimately, let me mention that in the recent years, also some non-perturbative construction of nets of C-star algebras satisfying some of these axioms has been done by the first paper was from Buchholz and Fredenhagen, and then there were contributions by other people, among which Kasia, for the Klein-Gordon and for the Dirac field. And here I should also mention that these dots are because many people has contributed to this, to the understanding of this first point here. Okay. Very nice. So this so far is still a bit abstract. How to make it more concrete? So we have this net of C-star algebras. We ultimately want to go back to our Hilbert space description, where we can compute scattering amplitudes, those that we measure in the LHC. And so this is done by specifying a state over these algebras. The state is a positive, normalized and linear functional. And once we have a state, the main result is that with the state comes up to unitary equivalence, a triple of Hilbert space, a representation and a vector, which allows to take this abstract net of C-star algebras and represent them concretely as bounded operators on a Hilbert space. Now I say bounded because I have a C-star algebra. Okay, and so we recover our Hilbert space description from this abstract setting. So we are happy with that, but we are also able to compare different states which might not be described inside the same Hilbert space at this instead abstract level. And of course, let me also mention that the Hilbert space for a specific class of states is exactly the Fock space that we are taught to work with, for example, on the free vacuum. Okay. Together, so to go even a bit more concrete, so I started with my net of C-star algebras. I have now represented it by a choice of a state. Then I can close it in the topology, in the weak topology on the Hilbert space, and get out of that a net of so-called von Neumann algebras that is related to the net I was starting with. And this is a local net again because they are labeled by my localization regions. And okay, this is the definition of what a von Neumann algebra is. Dan already said something before. Here I said weak, here I write strong, because in this case the two closures are equivalent. And now comes the feature of QFT, namely, or maybe let me say it like this. Already from a mathematical point of view, the understanding of von Neumann algebras was an interesting problem. Actually, it was an open problem that was solved and worth a Fields Medal to Alan Kohn. But still, making the long story short, if you want to understand the properties of von Neumann algebras, you should understand the properties of three types of factor von Neumann algebras, namely the type 1, the type 2, and type 3. Type 1 von Neumann algebras, again, to be a bit formal, are, for example, von Neumann algebras that describe systems of quantum mechanics, and that are, for example, among them, those that are generated by finitely many minimal orthogonal projections. For type 3 von Neumann algebras, recently, people here in the audience and working on some proposal that was done before by these other people. In the audience, I mean Chris, I mean Kasia, Dan, and other collaborators, proved or discovered that type 2 von Neumann algebras appear when describing a composite system in which you have a quantum field theoretical system coupled to an observer. The von Neumann algebras of this composite system are of type 2. And finally, if you just look at a purely quantum field theoretical system, well, you cannot avoid, actually, the fact that these algebras are of type 3. The local algebras are of type 3. And maybe I should mention it here, it will come back later. Besides this classification, type 3 algebras have a not so nice feature compared to type 1 algebras and so quantum mechanical systems, that they lack a notion of trace. And you will see in a second why this poses some problems and how these problems can be overcome. But before that, so I told you I wanted to talk about modular theory. So now I have my net of von Neumann algebras after having chosen a state. And modular theory is a quite natural property that you might get out of your von Neumann algebras by just choosing a cyclic and separating vector for that. Cyclic means this property, separating means this other property. A here is a generic element in the von Neumann algebra. Of course, I would like to discuss the case for my local net of von Neumann algebras. So the first question that you might ask yourself is whether such a cyclic and separating vector exists at all for the net of von Neumann algebras, and at least for Klein-Gordon fields, but also for other type of free fields. This is ensured by the Ricci-Leiter theorem, for example, for the vacuum. So if I take my vacuum state and I represent my abstract net with respect to the vacuum, well, then the Ricci-Leiter theorem ensures that the local net for the local von Neumann algebras, I have a cyclic and separating vector. With the cyclic and separating vector in my Hilbert space, then I can define the tomita or the relative tomita operator, which is associated to two such cyclic and separating vectors. By the way, once you have one constructing another cyclic and separating vector, it's not so difficult. And the tomita operator is essentially a closable operator that when acting on an element of the von Neumann algebra on the corresponding cyclic and separating vector just gives me the adjoint of that. And since it is invertible, I can polarly decompose it and get out of that two pieces of data. There are this modular conjugation, this J, it's an anti-unitary operator, and the modular operator delta psi, which is called the modular operator, and it is self-adjoint and positive. With these two pieces of information, so now, by just having my local net of von Neumann algebras and having picked one of these cyclic and separating vectors, I get for free two very nice properties that are an automorphism, so a sort of notion of time evolution at the level of the observables, which is called the modular flow, and a way to relate the von Neumann algebra to its commutant. And it's nice because it's built in. It's built in the setting. Okay. And now I would like to convince you that with modular theory you can actually do something nice for understanding the properties of the local algebras. The first point is Hug duality. So this tries to address the answer to this question, so whether the local algebra, so the local net, exhausts all observables which are consistent with the principle of causality. Why so? Well, and partially I already give you the answer here, in the sense that for sure you know that the geometric commutant, so the algebra localized in the space-like separated region is contained in the algebraic commutant of your net, because this is the axiom of causality. But the other inclusion is not granted in principle. So this is something that needs to be proven whether it is true. And it will definitely depend on your choice of state. So for example, for pure states, for example, for the Klein-Gordon vacuum, this inclusion has actually been proven, giving this equality that is known as the Hug duality property. Hug duality is essentially telling me that, well, I cannot add any other observable in my local von Neumann algebras without violating causality, because otherwise I will break this the inclusion of the geometric commutant into so the equality between the geometric and the algebraic commutant. And besides this more abstract statement, Hug duality is also a core property in the theory of superselection sectors. So what I did together with Leonardo was to prove this little theorem. It was expected in the literature, but we kind of worked out all the steps. Namely to say that if one considers the local net associated to the Weil-Sister algebra, so a free Klein-Gordon field on Minkowski spacetime, and one considers the representation with respect to the KMS state on full Minkowski, then a notion of Hug duality still holds at the price of taking into account that besides the geometric commutant, there is also a union with an additional algebraic piece of information that comes from the fact, essentially, that the KMS state, so the thermal equilibrium state, is not pure, so its representation is reducible. And you see immediately if these would have been the pieces of information of modular data and the representation for the vacuum, this quantity here would have actually been just the identity. That's why the two results are consistent with each other. Okay, so this is, and you see, in order to prove this result, it's crucial to use the tools of modular theory. That's the message that I would like to give. Okay, so this is the first part. For the second part, let's come back to the comment I did before. On type 3 for Neumann algebras, I don't have a notion of trace. So how can I describe entropy? How can I say that how if I have so in quantum mechanics, if I have a generic density matrix describing my state, then I can define the von Neumann entropy, the von Neumann Umegaki relative entropy between two such density matrices of states. But if I don't have a notion of trace on my von Neumann algebra, these two quantities are not computable at first. Of course, there are way out. One possibility is to introduce a cutoff in your theory, like I put it here as reference Patricia and Rick, for example, and collaborators, but there are many other ways. You can say, okay, instead of considering my system with these infinitely many degrees of freedom, I try to reduce them, get something concrete out of that, and then maybe study what happens when I try to remove my cutoff. It's of course much more operational and allows to make things concrete, while from a mathematical point of view, what you can notice anyway is that, okay, maybe something of this form might not be well defined in my setting, well, something of this form might not be well defined in my setting, but maybe something of this kind can still be well defined, essentially because I have a difference here, and if the kind of divergence for which these objects are infinite is ultraviolet, then since ultraviolet divergences in QFT are kind of universal, I can hope to still get something well defined for the relative entropy. And this was indeed true. It was proven by Araki and Ullmann separately, that proved that for two, let's say, seeking and separating vectors, their relative entropy can be defined as the logarithm of the relative modular operator. So again, modular theory is useful. You can actually get something out of that. In this case, the relative entropy. This is a generalization in the sense that it works on type 3 von Neumann algebras, but it reduces to the von Neumann Umegaki relative entropy on type 1 von Neumann algebra and has all nice thermodynamical properties. The only counterpart, of course, the main counterpart, is that it's very tough to have control on the relative modular operator and to compute something explicitly out of that. It's tough for the modular, it's even worse for the relative modular operator. So you look for some simplification. One of these simplifications is when
you consider two cyclic separating vectors differing by the action of two unitaries, one in the von Neumann algebra, one in its commutant, and then this expression here can be written in a more nice form that you have more control and you can get something explicitly out of. And this is exactly what happens for bosonic coherent states, is something that was very well studied in the literature, also in applications. So what we did together with Albert Much and Rainer Werch was to try to find some sort of counterpart of that in the case of fermionic field theories. So try to essentially reduce to that setting, so try to find a unitary operator in the Car algebra we can, for which we can compute the relative entropy explicitly, and this is what we did. So the long story short, just because I think I'm running out of time, is that if you choose properly the label of your Dirac fields, so with these two properties here, then you can make sure that the Dirac field, you have Dirac fields that are unitary operators actually, and with them then you can excite your standard vectors, so cyclic and separating, define the so-called single excitation states and compare them with the cyclic and separating vector, the standard vector that you were starting with. And the result is explicit in the sense that it depends just now on the modular operator of your starting vector, cyclic and separating vector. You can do the same also for multi-excitation, so instead of considering just one of these unitary Dirac operators, you can consider multiple of them, provided that their labels all satisfy this requirement. And maybe as an introduction to the last slide, let me say that while for coherent states many applications has been studied in the literature, for the fermionic case still, since it is a more recent result, there is not much. That's why I come to this slide, this future perspective. Okay, so the first thing that might be nice to do and that we are thinking to work on is to extend the result of Hug duality for generic mixed state, not just KMS states, and hopefully we expect to see at some point that maybe requiring these states to have also the Hadamard property will be necessary. Then, of course, try to understand the relative modular operator for more generic states. This is something that is already done in the literature. There are results, old results by Araki and Oy and Petz about perturbations of KMS states, where the perturbation is either an element of the algebra or it's affiliated to the algebra. There are results for generic quasi-free states, at least partial results, this recent paper, for example. And there are also cases in which you might say, okay, maybe I'm not interested in knowing the relative modular operator exactly, but I'm just happy with some bounds. And so if you're just happy with bounds, there are many results for more generic states. And then, of course, applications. So once you know how to compute things explicitly, you can go on and study, for example, relative entropy area variety in some setting can be related to a stress energy tensor. Why not? Try to infer something like a quantum energy inequality by the properties, the bounds that you have on the relative entropy. And of course here the list of references are just about more recent works that have appeared or those that I am more familiar with, but there are much more on the literature. You should go look into them if you're interested, or ask me. I will be very happy to tell you more. Thank you.
Thanks, Stefano, for the nice talk. Are there questions?
As it's late in the day, it's perhaps not an entirely serious question. So, all the way at the start, you said something about Ingvason's results of type 1 not being compatible with causality, and you called it Fermi paradox.
Yes.
Now,
I've heard of Fermi paradox as where are the aliens if we cannot see them? Is there any relation?
No, I think not. I think there is no relation to that. No. This is just, at least that's the way it is called in that paper, and I think there was an even earlier paper, not of Fermi, but of someone calling it, I don't remember the author, but calling it the Fermi paradox. Yes, it's essentially telling you that if you try to model a quantum field theoretical system with type 1 algebras, you can encounter some violations of causality. You're welcome.
Are there other questions? Maybe since we have 1 minute left, could you say something about the last result you were mentioning between relation between relative entropy and area?
Yes.
Yeah.
Okay, so this depends, of course, on the space-time on which you are working, but essentially, at least this work here, but I think all of them are based on the fact that for coherent states you can compute explicitly the relative entropy, and what you find out from that calculation is that this quantity here is intimately related to the stress energy tensor of this excitation that you're doing of this coherent, associated to this coherent excitation, and then you can relate the stress energy tensor via the Einstein equations to a variation of the metric, and from that get a variation of the area of the geometry via Rashaduri equation if the theory is massless. At least in the work that I did, the theory was massless, yes. Yeah.
Thank you. If there are no further questions, let's all thank Stefano.
No worries. Do you need help in that? No, not Ginger. Right. Oops. Yeah, I just, yeah, okay, thanks. Just a minute. There we go. Yeah. What's the second challenge? What do you have to do with this?
Yeah. Do you want me to keep it?
Okay.
It's,
I put this in my pocket because then I always drop it on the floor otherwise. Okay, great, thanks. Okay.
Okay, so our last speaker for today is Professor Emeritus Bernard Kay, also professor here in York, that we talk about the matter-gravity entanglement hypothesis. So okay. Please, Bernard.
Thank you very much. Yeah, and thanks, Patricia. Yeah, as the last speaker, let me particularly thank all the organisers, Patricia and Christiane and Filippo and Rick, for all their work and for the initiative to organise this series of conferences. Yeah. Yeah, so it's the last talk after a long day, but at least that I hope it will be easier to assimilate because it'll all be words and very few equations. But of course the words contain equations that you have to imagine. Yeah. Okay, so let's begin by reminding you that Stephen Hawking, yeah, let's see, how does this work? Yeah, Stephen Hawking's discovery nearly 52 years ago, which is incredible to me, that a black hole emits thermal radiation. It resolved some puzzles, but also raised some new ones. So on the one hand, it confirmed Bekenstein's hypothesis that a black hole has an entropy proportional to its area, and thus resolved J.A. Wheeler's puzzle that prior to Hawking, you could seemingly violate the second law of thermodynamics
by throwing entropic matter into a black hole. And it fixed the constant in front of the area to be a quarter. Instead, people now believe in a generalized second law which says that a quarter of the area plus the entropy of everything outside the black hole is the thing that increases. Okay. On the other hand, Hawking's discovery 52 years ago raised several new puzzles. Of course, there was let me call this number one, there was the information loss puzzle. That can mean different things to different people, but I think what people mean by it these days is the question how to reconcile a belief in the unitarity of quantum gravity with a semi-classical understanding of black hole formation and evaporation, where seemingly information must be lost on the future singularity. And let me remark that I will not address this puzzle in this talk, except to point out that semi-classical gravity may anyway not be an adequate framework to understand black hole evaporation, in which case this puzzle isn't necessarily something that should trouble us. Okay. But there are other puzzles. So there's a puzzle that has been stated by several people, for example, Wald and Page in certain review articles, that's called the thermal atmosphere puzzle. So supposing you imagine a black hole in an equilibrium state enclosed in a box in equilibrium with its Hawking radiation, then for a black hole in equilibrium in a smallish box, there is evidence, I don't have time to go into that, I could answer questions on it, that A/4 is the entropy of the gravitational field, but there is also evidence that it's the entropy of the thermal atmosphere. And if we were to add these two together, we would get A/2, which everybody agrees is the wrong value. So that's a puzzle. Okay. And the third, well, to explain the third puzzle, let me say, okay, but Hawking's discovery also raises questions about the very nature of entropy and the origin of the second law, with or without black holes. So for a closed system, excuse me, one can ask of a given, say, pure state, and here I'm thinking in the Hilbert space language, so I mean a pure density operator or a projector onto a single vector in a Hilbert space. So for a pure state, density operator rho, you can ask the question, what is its entropy and why does it increase? In other words, why does the second law hold? Okay. And traditionally, the answer to the first question is through something called coarse graining. We pick a set of macroscopic observables with the property that we can't distinguish between two states if the expectation values of all these observables are the same. And we then say that the coarse-grained entropy of rho is the supremum of the von Neumann entropies of all now mixed density operators, let's say rho hat, which have the same expectation values as rho for those particular observables that we picked. Okay. Then there are arguments that the coarse-grained entropy of a system initially out of equilibrium will increase. However, such a notion of entropy depends on that set of macroscopic observables that we picked, which depends on what we can and cannot distinguish, so it's subjective. However, okay, that's just a repeat of that sentence. On the other hand, Hawking's result that black hole entropy is an area, okay, divided by 4, suggests that there is nothing subjective about entropy, and maybe our whole understanding of the origin of thermodynamics prior to Hawking was wrong, and instead the entropy of a closed system is something objective that has to do with quantum theory and with general relativity. And Okay, if we pursue that suggestion, then what could be more natural than proposing that the entropy of a closed system is its matter-gravity entanglement entropy? That's a natural statement that involves quantum theory and it involves gravity. Okay, and that's a proposal I made nearly 30 years ago now, back in 1998, and I call my matter-gravity entanglement hypothesis, or MGEH, which I've been investigating ever since. Okay. Of course, I don't know any more than you do how to quantize gravity. I simply postulate that at least in a low-energy effective theory, valid for energies very much less than the Planck energy, but that could be very high energy, right, because the Planck energy is very big. At least in such an effective theory, one may take, so we just postulate that one may take quantum gravity to be an ordinary quantum theory on a Hilbert space, H total, which arises as a tensor product of a matter Hilbert space and a gravity Hilbert space. And we postulate that at every time your closed system of interest could be the whole universe, or it could be the system of a collapsing star that then forms a black hole and then evaporates to form by Hawking evaporation. One postulates that at every time your system is described by a pure state vector unitarily evolving in a Schrödinger picture according to some quantum gravitational Hamiltonian. Okay, so these are just very basic conservative assumptions that quantum gravity is a quantum theory of a normal type. Okay. So then I can argue several things. Okay, so first of all, this leads, I think, to a plausible understanding of the second law for a general closed quantum gravitational system. If we assume that the total Hamiltonian takes the form matter Hamiltonian plus gravity Hamiltonian plus interaction Hamiltonian, and if we also assume that for some, I admit, unknown reason, but let's assume it, that the initial state is unentangled or has a low degree of entanglement, then you would expect that due to the interaction, the entropy, as I define it, would increase monotonically. So that would be an explanation of the second law of thermodynamics for a general closed system. Could be the universe, but it could be the system consisting of a model star which collapses to a black hole and then Hawking evaporates. By the way, I mentioned at the outset that what we mean by the information loss puzzle has maybe not always been so clear or has perhaps changed over time. For me, years ago, I thought that was the information loss puzzle. How do you reconcile time evolution being unitary for that process where a black hole forms and then evaporates with the fact that the entropy increases? If you believe the entropy is the von Neumann entropy, that's a unitary invariant, and that's a problem. But if you believe that the entropy is matter-gravity entanglement entropy, that's not a unitary invariant, and it's very plausible that it would actually increase if the initial state had a low degree of entanglement. But anyway, at least we can say, sorry, I keep pressing the wrong button, at least the question of whether the second law holds on this view becomes a well-defined objective mathematical question about the quantum gravitational Hamiltonian and the initial state. Okay. So that's one point. Okay. I'm just trying to remind myself what was next in this talk. Yes, in the case of the model closed system consisting of a black hole, of a star that collapses through a black hole and then evaporates, I have recently argued in a couple of papers on the archive in 2022 that the final state after the Hawking evaporation of an initially large black hole will be a pure state consisting of mainly of roughly equal numbers of photons and gravitons entangled with one another, and that this will have a bigger entropy, as I define it, so matter-gravity entanglement entropy, than the initial black hole, okay, consistent with the second law. Okay, so this was a general argument for the second law holding, but one wants to put some flesh on that and understand how it actually works out in detail, and this is how I think it actually works out in detail for that system of a collapsing star that Hawking evaporates. I don't have time to explain all my reasoning here, but let me just mention some ingredients in it. This depends on there only being, maybe surprising point, and maybe you could say worrying point, but we can debate that, is that this argument depends on there only being two massless fields in nature, the graviton and the photon, both with the same number, 2, of helicity states. And an ingredient in this argument, so this is hopefully to tempt you to read the details in these papers. An ingredient in this argument is that based on some work I did back in 2012, if you look at a random total pure state of quantum gravity with a given amount of energy in a box, you can argue that it will most probably be, okay, so first of all, at low energies, it will most probably be a maximally entangled state of mostly photons and gravitons in roughly equal numbers. And then at higher energy, you'd expect it to look like a black hole surrounded by an atmosphere of mostly photons and gravitons entangled, as in one. Okay, but that's just, as I said, to give you some of the flavor of that work, but you'd have to read these, well, in fact, it's an essay, and I'm still working on the detailed details of that. Okay. And this is what prompted me to think of this matter-gravity entanglement hypothesis in the first place. Our matter-gravity entanglement hypothesis also offers a resolution of the thermal atmosphere puzzle that I mentioned earlier. So we assume that our black hole equilibrium in a smallish box is in a total pure state. Then the entropy, as I define it, matter-gravity entanglement entropy, is of course the same thing as the von Neumann entropy of each of the partial states of matter and of gravity separately, which in a smallish box you can argue is roughly the same thing as the von Neumann entropy of the thermal atmosphere and the von Neumann entropy of the black hole. Okay, the thermal atmosphere won't quite be the same thing as the matter because a little part of it will consist of gravitons. Okay, but it's roughly the same thing. So if we ignore that small difference, then you see this seems to explain why the entropy seems at the same time to be entirely the entropy of the gravitational field and entirely the entropy of the thermal atmosphere. Okay, thanks. That the total state is pure but highly entangled also seems consistent with the mixed partial states of gravity alone and of matter alone being approximately thermal at the Hawking temperature, because of course you can have a total state which is pure, but when you trace, you know, it on a bipartite system, right, matter and gravity, but when you trace over one of those parts, it can have a very big entropy, and it could be almost thermal. Okay. I also have arguments as to why, according to this hypothesis, the entropy of the black hole equilibrium in a box goes like a constant times the energy squared. So that's roughly in agreement with the fact that, you know, black hole entropy, say for a Schwarzschild black hole, goes like the area, which goes like the square of the mass, right? Which is a very big increase. that increases faster with energy than entropies of ordinary matter, right? M squared is an unusually fast increase, and I have arguments why for that, and also arguments why those partial states are actually approximately thermal. And these arguments are based on, but also critique, the string theory calculations of black hole entropy that go back to Susskind in 1993 and Strominger and Waffer's famous paper in 1996. So it's easier to tell you about what my critique of that work is than to tell you about how I make use of that work. So let me sketch that first. To sketch the critique part first, and let's look at Susskind and Horowitz and Polchinski. I could also tell you what I think is not satisfactory about this, but let's leave that for questions perhaps. To sketch the critique part first, these authors relate the entropy of a Schwarzschild black hole to, as they put it, the logarithm of the density of... It's a very simple point. The logarithm, they relate it to the logarithm of the density of states of a long string, which they argue is the weak string coupling limit of a black hole. But of course, the density of states of any system is not a dimensionless quantity. It has dimensions of 1 over energy. So this requires an unknown length scale or energy scale to make the argument of the logarithm dimensionless. And so it gives an ambiguous answer. And that, for me, is a problem. Instead, what I do is I look at the entanglement entropy between a long string and its stringy atmosphere in a random total pure equilibrium state with a given amount of energy in a box. And no such ambiguity arises for this. But you get a similar answer, and essentially, you know, doing this calculation fixes that length scale that even in principle Horowitz and Polchinski weren't able to fix. Okay. So just, I have very little time, but just to sort of, this is my slide for that discussion. So very quickly, what these people did is they said, well, if you scale the string coupling constant G down and the string length scale L string up, keeping Newton's constant fixed for a black hole, and this is assuming you can do things in string theory in 4 dimensions. It's sort of not, you know, it's partly, what's the word, heuristic. If you do that, they argue that a black hole becomes a long string, and then they relate the entropy of this to the entropy of that. And my modification is that what you should really do is start with this black hole in a box in a thermal atmosphere and do the same scaling story. And what that will go over to is an equilibrium with a long string in contact with a stringy atmosphere. And then you calculate the entanglement entropy of these things. Okay, thank you. Okay, so just very quickly, one then argues just to finish that topic, oversimplifying that for a random total pure state with energy E of the long string stringy atmosphere system, the partial states of long string and stringy atmosphere alone will each probably be approximately thermal. Yeah, so this is how you argue that that's consistent with this proposal for the solution of the thermal atmosphere puzzle, will be approximately thermal, and their entanglement entropy will probably go like a constant. I should have put a factor of the string length scale L in here, which translates by an argument similar to that given by Horowitz and Polchinski to the black hole in its atmosphere being thermal, and their entanglement entropy going like constant times E squared. The point is that you argue that, I mean, this is Horowitz and Polchinski's idea. You argue that this string length scale that I should have put in there gives you another factor of E. Okay. Okay. Next topic, E. you might ask, okay, well, I've got a theory for the entropy of a closed system, but what about open systems? When I first made this proposal, people emailed me and said, you're surely not suggesting that the entropy of a hot cup of coffee is due to its entanglement with gravity. And I didn't know the answer straight away, but I think this is the answer. So I think for a hot cup of coffee, the way you should understand the fact that it's hot is with the traditional environment paradigm. So not coarse graining, okay, but you understand that your open system or your hot cup of coffee is in a mixed state with a lot of entropy by the fact that it's coupled to an environment, and maybe the total system is in a pure state, but it's entangled with the environment, and when you trace over the environment, that gives you the fact that it's actually in a mixed state with a lot of entropy. Okay. The problem with the traditional environment paradigm is if you imagine what happens to thinking of the entropy as a function of x, where x is the sort of position of this partition between system and environment, if you let the system grow at the expense of the environment until it fills the whole box, but you've assumed that the total state is pure, the entropy as a function of x might go up, but then it'll go down to 0. So the entropy of your whole closed system will be 0. Okay. So what I think is natural to extend my hypothesis to open systems is to say that this picture should be replaced by a picture like this. So you've got a dividing line between gravity and matter here, and then you've got another movable dividing line like this one between what you regard to be your matter system, so this is now your cup of coffee or something, and what you regard to be your matter environment. And you define the entropy of your matter system as what you get by tracing this overall pure state of the total system, both over the matter environment and over gravity. And if you do that, then of course, if you plot the entropy of this matter system as a function of x, it will go up, but it won't come down. Okay. Yeah. So I can stop there. As a final topic that I could have discussed, I could give a little discussion comparing and contrasting our picture with that of Page, which Lawrence talked about in his talk. But I could save that for the questions and stop there. Okay. That's the end then. If anyone wants to ask, how do you compare your proposal with that of Page? But that's something else. Yeah.
Yeah, there. Yeah.
I'm sorry, I will ask a different question.
Good.
But I have two questions. Maybe one of them coincides with Kasia's. But is it entirely... So you said your gravity matter entanglement entropy is objective, which is I suppose, a very big thing going for it over coarse-grained entropy. But is it entirely obvious how you distinguish between what is, let's say, a gravity degree of freedom and what is a system degree of freedom? Because, I mean, turning in this measurement scheme, sort of the late time identification and the early time identification of, let's say, an interacting field with its sort of non-interacting component is not the same. So therefore,
I agree.
So at some point you did say something about, I assume that at early times there is no entanglement. So this may suggest that actually you're looking for an early time identification between the non-interacting and the interacting settings somehow, or maybe anyway. This is basically
well, let me say a couple of things. I mean, first of all, I mean, I think that there's at least two senses in which there's a problem. What do you mean by this division of things into matter and gravity, right? So I think One point is that maybe at very, very high energies in quantum gravity, whatever that is, there is no clear separation between matter and gravity. I mean, you could imagine that you know, as the universe evolves from the very early times before 10 to the minus 43 seconds, there's some sort of phase transition where, just like the later phase transitions, where matter, there's a time when energies are sufficiently low when that distinction becomes meaningful. So that's one point. And another point is, yeah, I appreciate there's a difference between bare fields and dressed fields. And for example, you know, a physical electron is a bare electron with a cloud of photons and so on. And presumably there's similar stories going on with gravity. But still, you know, I think if you look at particular concrete situations, thought situations, in some situations, I think you can identify what, or you can convince yourself that it's possible to identify what you actually mean by physical gravity and what you mean by matter. Many years ago, Mike Duff, I've just come into my head, but I think this is very relevant. Many years ago, Mike Duff wrote a polemical article saying all of quantum field theory in curved spacetime is nonsense because you can't separate gravity from what you mean by the classical gravitational field from what you mean by quantum fields on it. And he gave an example, which is you can do an example where you do a Lagrangian for the Einstein coupled to a scalar field, and then you do a field transformation where you put a conformal factor in your scalar field, and then you get Einstein coupled to a different scalar field with a different conformal, what's it called, non-minimal coupling term. And so, you know, he argued that doing quantum field theory in curved spacetime is nonsense, but I don't think it is nonsense, and I think analogously to that, it's not quite the same question. I think it can make sense in some situations. I mean, for instance, in that concrete situation, suppose you take a box. Suppose you just imagine there's only Einstein and Maxwell and none of all those other annoying things like Dirac equations. And you imagine that's your theory. And of course, there is some interaction between them. And you put it in a box. Imagine, and of course, you also have to imagine that that box is capable of containing gravity waves, which is a bit dubious. But grant me all that, then, you know, if you give that a certain amount of energy, you can make quite a watertight argument that you can look at a random pure state where you're looking at the invariant measure on the space of unit rays in your total Hilbert space. You can make quite a serious, detailed argument that with an overwhelmingly high probability that if that energy is not too big, what you will have is an entangled state of gravitons and photons. If the energy is then much bigger, you expect a black hole to form, and then things get more complicated and less well understood. I agree. Yeah.
Okay, we have time for last question from Patricia.
Hi, Bernard. Thank you very much for the wonderful talk. I had actually 2 questions. Is that possible?
For me, it is. I don't know about the chairman.
Only one? Okay.
And everybody wanting to go to the pub.
Okay, fair enough.
You can ask one in the pub.
Okay, I will ask you the second one in the pub, but I want to make you happy, so I would like to ask about how to compare with Page.
Oh, yes. Well, okay, thank you. Well, very quickly, you see, for me, I mean, Page never quite spells this out quite in our sort of axiomatic language that we like, but you know, I said we have a total Hilbert space which is a tensor product of a gravity Hilbert space and a matter Hilbert space. What he's basically doing, and of course his own, I mean, my thing I claim applies to lots of different kinds of systems. He's just interested in that one system, which is a star that collapses to a black hole and then evaporates. And he assumes that you can write the total Hilbert space of that system as a tensor product of a black hole Hilbert space and a radiation Hilbert space, where for him radiation is what's outside the black hole. But as he admits himself, he immediately gets himself into, well, there's several points to be made. So one of them is that he immediately gets himself into a problem about separating this black hole and the radiation, because he doesn't want them to be entangled. According to Page, when a black hole first forms, the radiation is in a vacuum state and the black hole is in a pure state. That's what Page says. It's very, it's very different. And all that entanglement, he actually says, well, we have to make the boundary between the black hole and the radiation a fuzzy region, and we mustn't be too definite about it, and that way we avoid dealing with the entanglement. If we put in a sharp dividing line in our manifold and said to the left of that is black hole close to the horizon, and to the right of that, everything to the right of that we call radiation, then you'd have massive amounts of entanglement across that boundary. And he doesn't want to have that. He wants to get rid of that. Whereas for me, that entanglement is kind of what the black hole entropy is. Basically, it's not quite the same as entanglement between matter and gravity, but it's closely related to it. Matter entanglement between what's to the left and what's to the right of that boundary. And for me, the entire entropy of the black hole is that entanglement entropy, which Page throws away before his scheme can start to make sense. So he does that straight away. What have I written here? There's several people. Oh yeah, and then there's the point, as several people have argued, that by the Page time, he still assumes that although he's kind of doing quantum gravity at one level, on the other level he's insisting that at every time as this system evolves, there's still a valid semi-classical description where you've got a black hole with a definite mass and radiation with a definite amount of energy. And then he kind of replaces those with quantum things. But, I mean, from a general quantum mechanical point of view, you wouldn't expect that. You'd expect you've got a sum of states, a superposition of states like black hole with energy, with one energy, times radiation with the complementary energy, plus black hole with a different energy, times radiation with a different energy, or black hole with one shape, times one bit of radiation, plus black hole with another shape, times another bit of radiation. So you might expect that by the time you get to the Page time, the semi-classical description has broken down, and the horizon, or the black hole, whatever you think about, has become a very quantum fluctuating thing and doesn't have a classical description. But Page and all these people who follow him, like Maldacena et al., insist that it's not like that. And in fact, they say that they have something that they call the fundamental dogma, which is that everything is semi-classical down until the very, very late stages of black hole evaporation, when the black hole has gone down to the Planck mass size or something, which is long after the Page time. Okay, so those are some points. yeah, that's the point I made about this fuzzy blah blah. Yeah, but anyway, you know, just to sort of, without being disparaging, just to sort of summarize the differences, the Page scenario talks about two different entropies, the von Neumann entropy and the coarse-grained entropy. And it focuses on how the question of how the von Neumann entropy of the radiation, from their point of view, goes to zero at late times, which they claim solves, if they can show that, they've solved what they think is the information loss puzzle. Whereas, and if you ask them, well, what about the second law, they just appeal to coarse graining, but I didn't see where they sort of worked that out in detail. Whereas I take it as axiomatic that the von Neumann entropy of the total state is always zero, or it follows trivially from the axioms that that would be the case, including after the evaporation, when it may be identified with the von Neumann entropy of the radiation, because by that time the black hole isn't there anymore. And for me, the interesting question is to understand, without vague subjective coarse-graining ideas, how the physical entropy nevertheless increases. And as we said, this leads to the prediction that the final state consists mainly of photons and gravitons in a highly entangled state. If the initial black hole is a big black hole, so for most of its radiation is very low energy. Yeah. Okay.
Okay, let's postpone further questions to the pub, and let's thank Bernard.
Do you want to say something?
Maybe Patricia and Christiane?
So I can say some final words, I guess, just to finalize everything. Bernard, thank you so much for your talk. I have some questions for the pub, so you're joining us, right?
I am joining you.
Good. So let me just then say some final remarks before the final remarks by the organizers. So let's start by thanking Patricia and Filippo and Christiane for having organized this. So thank you so much. Let's thank the organizers. So I started my PhD in 2020. In 2020 was when the FV framework started being developed and things like this, right? That's when I first heard about research being done here in York regarding quantum field theory and all this. And it's just so nice to see how the research has progressed. I mean, Kasia used to be a young professor back then, right? Now it's a very experienced, a young professor used to be. Now you're an experienced professor, still young. But it's just very nice to see how the research is becoming more, I don't know, I would say, touching more into quantum information, into quantum foundations, into quantum reference frames, more broad overall, Bell inequalities and all this. And now semi-classical gravity with more recent additions to the team here. So it's very nice to see all of this. So I think that this was a very, very nice display of the research being done in New York. So it was a pleasure to watch everything. So just to end then the circuit here, let me just remind everyone that next week we'll be in China. So the time zone might be very weird to watch most of the conference, but if you want to join online, feel free to. But regardless, we will have a circuit in Hangzhou in China, and looking forward to that too. And I'll see people online next week, and hopefully you guys can enjoy some of these talks too. So thank you.